What's good? What's good? So, yeah, hopping back in where I left off. What are transformers? Learn about what transformers are. Key ideas: transformers are a type of neural network architecture developed in 2017. They scale well with data, i.e., bigger the data, better the models. Transformers are data agnostic and work well with many different data types, including text, image, audio, etc. They're good at transfer learning. So let's watch this.
GPT stands for Generative Pre-trained Transformer, and it's the transformer part that we're going to be focusing on in this lesson. But before going over what they are, let's provide some context. If you've ever played around with ChatGPT, then you've already interacted with an application powered by a transformer called GPT-3, or possibly even GPT-4. GPT-3, or any GPT-associated models, are from a family of transformers that are designed to predict the next element in a sequence based on what came before. You know those moments when you and your best friend finish each other's sentences? Well, your best friend is also your very own personified transformer model. What are transformers, though? They are a specific type of neural network architecture introduced in 2017 that models like GPT use in implementing pre-training and fine-tuning. For the uninitiated, neural networks are computational models inspired by the brain, consisting of layers of nodes or artificial neurons called the input, hidden, and output layers. It learns from the data in the input layer, adjusting weights between the connections of each node in the hidden layer to make predictions for the output layer. As the number of layers in a neural network increases, so does its complexity. These complex neural networks belong to a subset of machine learning known as deep learning. The increase in complexity allows for more intricate learning, enabling neural networks to tackle tasks like natural language processing, or NLP, and computer vision. Additionally, model performance in deep learning models scales with data, so the bigger the training dataset, the better the models. The neural network architecture of transformers has allowed it to be successful when applied to many different types of data, such as text, video, audio, image, and even protein sequences. In other words, they're data agnostic. They can even be multimodal and incorporate two or more data types at once, like in speech recognition, which combines audio and text. These models find application in various domains, including NLP tasks such as text summarization and sentiment analysis, as well as computer vision tasks like image generation and object detection. However, this course will primarily focus on their importance in NLP applications, particularly in the realm of language models. One of the things that makes transformers very powerful is their capacity to perform transfer learning. It involves two steps: pre-training and fine-tuning. During the pre-training step, transformers acquire a general understanding of patterns within the data. Typically, this involves having a large corpus of a specific kind of data: image, audio, video, and in the case of GPT, text from the internet, books, etc. Fine-tuning allows for the model to acquire specialized knowledge or to tailor a model to a new task. For instance, in the case of image data, an example of a pre-training task would be training a model to identify automobiles in images, and a fine-tuning task would be to identify trucks on a dataset with pre-labeled images of trucks. The knowledge acquired by the pre-trained model is transferred, hence the name transfer learning. In the case of language models,
Just gonna copy that. So pre-training task example for image data might be identifying automobiles. Fine-tuning task example might be identifying trucks. Pre-training task example with text data might be acquiring the ability to generate English language sentences. And a fine-tuning task example might be acquiring specific expertise in mimicking Shakespeare. More broadly, pre-training is learning a representation from a massive data set. Fine-tuning is retraining on a smaller data set to acquire specialization. Pre-trained language model, training can be done on a single GPU, money and compute, easily reproducible. Fine-tuned language models, so they're more reproducible, cost some money and compute. It seems training can't be done on a single GPU. This is a strange image, but regardless.
they can often be customized to acquire domain-specific knowledge with significantly less effort than training from scratch.
Nice. Okay, good. Back here, turn this down. So, on to the next. There's another one. Traditional versus neural language models. Learn about the differences between traditional count-based language models and neural language models. Key ideas: traditional language models struggle to capture long-range dependencies. Prior to transformers, neural language models based on recurrent neural networks or long short-term memories were attempting to solve this. Transformers use something called a self-attention mechanism to assess all parts of an input sequence. So let's bring the audio back in. Right there is good.
Let's distinguish between older language models, which were count-based, and newer language models, which are neural network-based. Traditional language models grasp the patterns and relationships within a language by analyzing large amounts of text data, often using n-gram models and statistical techniques. However, these count-based language models suffer from fixed context windows and thus struggle with long-range dependence, or LRD, which refers to a system's ability to capture relationships and dependencies between elements that are far apart in a sequence. If that's a bit difficult to understand, let's walk through a small example. The concert was amazing. The atmosphere at the venue was out of this world, and the crowd couldn't stop cheering. Understanding why the crowd is cheering depends on the knowledge gained in the prior sentence about the concert, specifically that the concert was amazing. The more words we throw in between these two sentences, the longer that LRD becomes. Count-based language models would have an increasingly difficult time capturing the relationship between the concert and the cheering. This is where neural networks come in. Prior to transformers, two other types of neural network architectures served as a stepping stone towards solving LRDs. These are RNNs, or recurrent neural networks, and LSTMs, or long short-term memory networks. Today's state-of-the-art large language models employ transformers to enable self-attention mechanisms. This approach enables the model to assess all words in the input sequence when processing each individual word. During this process,
Let's pause that. So transformer-based large language models. Transformers capture LRDs using self-attention mechanisms. The model assesses all words in an input sequence while processing each individual word. Each word is assigned weights based on its relevance to the others. The graphic on the right is from the paper that introduces the self-attention mechanism cited here. Advances in neural information processing systems. Oh, no. Attention is
Thus, each word will be assigned weights based on their relevance to
the GOAT. So
each other.
cool.
This capacity allows large language models to efficiently capture LRDs and grasp the context and relationships among different words, overcoming the smaller language model constraints.
Cool. So, moving on. Is it another video? Yes, there is. I might as well just keep that audio on. History of transformers. Learn about the history of transformers and how the model sizes have been steadily growing since 2017.
While the Transformers architecture was introduced in the paper Attention is All You Need by Vaswani et al. In 2017, Transformers as language models came a year later in June 2018, when OpenAI released the first iteration of the Generative Pre-trained Transformer, also known as GPT-1. This model was the first of its kind, being able to generate coherent and contextually relevant text. 4 months later, Google also entered the LLM space in October of 2018 with their bidirectional encoder representations from Transformer Model, or BERT. BERT was designed to understand relationships and dependencies between different parts of text, being able to assist with sentiment analysis, named entity recognition, and extractive question answering. 2019 saw rapid improvements and iterations of the original 2 models, with GPT-2 having been released in February and Distill BERT, a lighter and faster version of BERT, in October. Notably, October also saw the release of 2 language models that implemented the original Transformer model introduced in the 2017 paper, namely Facebook's BART and Google's T5. These 2 models differed from GPT and BERT by being better suited for tasks revolving around text generation in relation to a provided.
Okay, so just to read it, right? In February 2019, GPT-2 was released and is 10 times the size of GPT-1. In October 2019, Distill BERT, a lighter version of BERT, is released by Hugging Face. October 2019, 2 sequence-to-sequence models, Facebook's BART and Google's T5. And here we see, in 2018, GPT-1 and BERT, 2019, GPT-2, XLNet, Distill BERT, 2020, T5, GPT-3, BART, 2021, GPT Neo, Megatron, Turing, NLG, and Claude, 2022, Palm, OPT, Bloom, Galactica, and 2023, Llama, Palm, Llama 2, Falcon 1080B, Mistral 7B. Feel like they're forgetting something awfully important in 2022, but maybe you can guess what that is. Anyway, let's continue.
Input, such as summarization and translation. From then on, the model sizes were steadily growing, but were still of the order of a few billions of parameters until 2020. From 2020 and on, we saw the size of these models grow exponentially. GPT-3 came out in May of 2020 with about 175 billion parameters, having been trained on 45 terabytes of text data. For context, GPT-2 had 1.5 billion parameters, while GPT-1 weighed in at only 0.2 billion. Parameter sizes of transformer models have been trending upwards since their inception. This is because their performance scales with the size of training data and compute available. 2022 saw the announcement of Google's Lambda, which specialized in conversation response generation. And later, in November of 2022, OpenAI released ChatGPT, a chatbot built on the language model of GPT 3.5, and that was made publicly available for a limited amount of time. Fast forward to 2023, and GPT-4 released with rumors estimating 1.76 trillion parameters.
Crazy times. We got another video. So we do, how do they work? Learn about how transformers work. Key ideas. The transformer architecture contains 2 types of neural networks, encoders and decoders. Transformer models can be encoder only, decoder only, or contain both. The primary difference between encoders and decoders is how their self-attention mechanism operates.
The original transformer architecture, as proposed in the 2017 research paper, consists of 2 main components, the encoder and decoder. But transformer models can be encoder only and decoder only as well. Let's see what that all means now. Encoders and decoders are both neural networks with many layers that can do interesting things with mathematical representations of input data known as embeddings. Both have a special set of layers known as attention layers that learn from training data through a mechanism known as self-attention. The attention layers help the model understand on a deeper level how each part of an input sequence relates to the other ones.
So let's pause there. What are encoders and decoders? They are both neural networks with many layers. They work with input data that's been converted to embeddings. They have attention layers. They learn from training data through a mechanism known as self-attention.
The main difference between encoders and decoders are in how they approach self-attention. Before we talk about what an embedding is, we should first discuss what tokens are. A token in language models is a set of words or subwords that text gets broken into. They are essentially the ingredients of a sentence. But just because we have the ingredients doesn't mean we have the recipe. By their own, transformers have no idea what to do with these ingredients, which is where embeddings come in. A big part of the field of natural language processing involves converting text into mathematical inputs that an algorithm can understand. An embedding is a mathematical representation of text that tries to preserve its meaning and context. Typical word embeddings based on neural networks capture underlying similarities within text. For instance, the words lion and tiger should have embeddings that are mathematically close to each other, and so would strawberry and apple. But strawberry and lion would be further apart. Self-attention is an iterative process where the model learns rich contextual information about the role of each part within a sequence. Input embeddings are first given positional encodings, so we know where they are in the input sequence when they are fed into an encoder or a decoder. A key aspect of doing this involves hiding a part of the sentence that a model needs to predict and asking it to guess where it could go.
Let's pause there. So how does self-attention work? Self-attention helps the model learn contextual information. Input embeddings are first given positional encodings when they're fed to an encoder or a decoder. Positional encodings tell us where something is in an input sequence.
This is known as masking in language models. Encoders randomly mask parts of the input sequence in a chunk of text given to them and train the model to predict those parts. This makes them great at tasks that require an understanding of the entire sentence. Attention layers can access inputs on both sides of a random mask. These transformers thus have bidirectionality, i.e. the ability to move to either side of the sequence that they're trying to predict. This is how an encoder-only model like BERT got its name. BERT stands for bidirectionally encoded representations from transformers. Decoders mask words during training in a way that everything after the words or phrase that they need to predict is masked. This makes them really good at completing sentences. Attention layers here, at any given instance, can only access words before the mask and have no access to the text that comes after.
Let's pause there. Decoders, masking mechanism. Everything after the token to be predicted is masked. They're great at text generation, and this is what makes them generative. During training, attention layers and decoders are only allowed to access tokens before the mask and none after. This makes them great at guessing the next best thing to say, i.e. text generation.
After. They're pretty great at text generation, and this is what makes them generative. This is how GPT models got their name. Recall that GPT stands for Generative Pre-trained Transformer.
Nice. Types of transformers. Learn about the different types of transformers. Key ideas. The three basic transformer types based on their architecture are autoregressive, GPT-like models that have a decoder-only architecture, autoencoding, BERT-like models that have an encoder-only architecture, sequence-to-sequence, BART, T5-like models that have an encoder-decoder architecture.
We're now beginning to get an idea of how we might already have a few different kinds of transformers based on their architecture. Let's dive into them now. The three basic transformer types based on their architecture are autoregressive, or GPT-like models that have a decoder-only architecture, autoencoding, or BERT-like models that have an encoder-only architecture, and finally, sequence-to-sequence, or BART or T5-like models that have an encoder-decoder architecture. Autoencoding transformer models are encoder-only. They specialize in tasks requiring contextual understanding, such as sentiment analysis, named entity recognition, which is the process of identifying and classifying specific people, places, or things, and extractive question answering. Autoencoding, and finally,
let's go ahead and read some of these, right? So autoregressive transformer architecture, decoder-only, suitable language tasks, text generation. Examples of autoregressive are GPT-2, GPT-3, Llama, Control Alpaca. Autoencoding, transformer architecture encoding only, suitable language tasks, sentence classification, named entity recognition. Examples are BERT, Distilbert, Albert, Robert, or Roberta, and sequence-to-sequence, which transformer architecture, encoder-decoder, suitable language tasks, summarization, translation, T5, BART, Pegasus, Marian MT, Uni LM, Ernie 3.0.
Finally, sequence-to-sequence, or BART or T5-like models that have an encoder-decoder architecture. Autoencoding transformer models are encoder-only. They specialize in tasks requiring contextual understanding, such as sentiment analysis, named entity recognition, which is the process of identifying and classifying specific people, places, or things, and extractive question answering.
So let's see. Input. Hugging Face is a great place to learn about AI and ML. Hugging Face, great place, learn AI and ML. So this captures context bidirectionally to understand that Hugging Face is a place, not a verb. And then the output, Hugging Face in an organization, great place, non-entity, learn, non-entity, AI is a subject and ML is a subject.
To do this, autoencoding models capture context bidirectionally. The attention layer of the transformer model considers all word in the input when processing each element. If we were to task a transformer model to recognize the entities of a sentence like Hugging Face is a great place to learn about AI and ML, then its attention layer will allow it to recognize that Hugging Face is an organization, not an emoji nor a verb, and that the abbreviations AI and ML stands for the subjects, artificial intelligence, and machine learning. Autoregressive transformers have a decoder-only architecture and specialize in text generation. These models are essentially feed-forward models that generate the next element in a sequence based on predicted probabilities giving the preceding elements.
Let's zoom by that, right? So autoregressive, decoder-only architecture generates the next token based on predicted probabilities given the preceding tokens, specializes in text generation, e.g. GPT. So if we have the cat, it'll make a prediction. The highest probability next word is chases with a 0.5, eats has a 0.4, and speaks has a 0.1. So after chases, the next highest probability is a mouse with 0.5, or a bird with 0.35, or a llama with 0.05. So if it sees the cat, it will predict the cat chases a mouse.
These models are essentially feed-forward models that generate the next element in a sequence based on predicted probabilities giving the preceding elements.
Feed-forward models that generate the next element in a sequence given the probabilities associated with preceding models or something.
Sequence-to-sequence models are encoder-decoder models that specialize in tasks that involve transforming one sequence of data into another, such as translation, text summarization, and generative question answering.
Sequence-to-sequence encoder-decoder architecture. Encoder processes the input, and decoder generates the output, specializes in transforming one sequence of data into another, e.g. part, which can take these characters and translate them. So the encoder takes in these input characters, and the decoder translates them into knowledge is power. And
we can provide a sentence in Hindi, and the transformer will feed the text first through the encoder and then the decoder before it starts outputting the English translation, knowledge is power.
Nice. What's next? In this lesson, we've discussed the history of transformer models, their applications in NLP and briefly non-NLP spaces, the inner workings of a transformer, and the 3 transformer categories. In the upcoming sections, you'll take this knowledge and apply it by implementing a few of Hugging Face's transformer models. Hugging Face has a plethora of open source models and datasets for learners like us to work with, including text-based transformer models, computer vision models, audio models, and tabular models. Consider it as a launchpad for your exploration of transformer models and generative AI.
So what's next? In this lesson, we've discussed the history of transformer models, their applications in the NLP and briefly non-NLP spaces, the inner workings of a transformer, and the 3 transformer categories. In the upcoming sections, you'll take this knowledge and apply it by implementing a transformer of your own using one of Hugging Face's transformer models. Hugging Face has a plethora of open source models and datasets for learners like us to work with, including text-based transformer models, computer vision models, audio models, and tabular models. Consider it your one-stop shop for all things AI ML.
Nice. Okay, so now I'm going to go ahead and turn this down. Come back here. So fill in the blanks in the following paragraph about self-attention in transformers. Self-attention is an something process where the model learns rich contextual information about the role of each part within a sequence. I'm going to guess iterative process. Maybe masking. Input embeddings are first given something so we know where they are in the input sequence. That's positional encodings. So we know where they are in the input sequence when they're fed to an encoder or a decoder. A key aspect of doing this involves hiding a part of a sentence that a model needs to predict and asking it to guess what could go there. This is known as masking in language models. So is self-attention an iterative process? Yes. These don't make sense, so I'm going to guess those are right. Cool. What do transformers play? What role do transformers play in GPT-like models? GPT models utilize transformers exclusively for pre-training with minimal involvement in the fine-tuning step. Transformers drive both the pre-training and fine-tuning stages, ensuring comprehensive contextual comprehension and language generation. Transformer focus on, no, okay, so it's this one. What is a distinctive feature of transformer models highlighting their architectural design? Highlighting their architectural design. Transformer models utilize pooling layers as the primary mechanism for feature extraction. Transformer models are characterized by attention layers, a key architectural component. Transformer models employ convolutional layers, so it's attention. That's all you need, baby. More precisely, multi-headed self-attention is the crucial distinctive ingredient of transformer models. That's multi-headed self-attention. Fill in the blanks in the following paragraph about decoders. Decoders mask words during training in a way that everything, something, the words, phrase they need to predict is masked. This makes them really good at completing sequences. So decoders mask words during training in a way that everything after the words, phrases they need to predict is masked. Believe that's true. Something layers here at any given distance can only access words. I'm gonna guess attention layers here at any given distance can only access words, something the mask, and have no access to text that comes something. Something feels off, right? Decoders mask words during training in a way that something that everything something the words phrase they need to predict is masked. This makes them really good at completing sequences. So if I was trying to predict the word in here, I'd want to mask all of that stuff because I want to see this stuff. Else, how am I going to predict it? So after makes sense. Attention layers here at any given instance can only access words before the mask and have no access to the text that comes after. Yeah, that feels right. Okay, cool. Which of the following statements about encoders and decoders is false? Encoders have attention layers where decoders do not. I believe that's false. Encoders and decoders have feed-forward layers in their neural network architecture. That's true. Attention layers and encoders can access both sides of a masked token. That might be false. Encoders have a random masking mechanism. Okay, that's true, and this is true. Now, which one is false? Is it true that or false that attention layers in encoders can access both sides of a masked token? I think that's true. Encoders have attention layers. Yeah, that's false. Correct. Cool. Which of these tasks suit auto-encoding models? Sentiment analysis, text generation, text summarization, translation. So auto-encoding, I believe that is sentiment analysis. That's correct. Transformers are best suited for text. They don't work as well with image or audio data. True or false? It's false. Correct. Transformers are data agnostic and work well with sequential data of any type. Let's go. What's up? What's up next? Let's code. Welcome. In this lesson, you will learn about Hugging Face's Transformers package and how to use it to implement language tasks such as sentiment analysis, text generation, and summarization. Starting from scratch, you'll learn how to use the pipeline object for model inference, how to perform text pre-processing and tokenization prior to using transformers, how to choose the appropriate tokenizer and model configurations, how to interpret model cars and choose the right model, how to perform different language tasks with encoder only, decoder only, and encoder decoder models, how to change parameters for model inference and text generation tasks. This lesson is intended to serve as a launchpad for your own exploration of Hugging Face's excellent suite of models and datasets. Here are some helpful tips to maximize your success in this course. We will be working with Jupyter notebooks and loading transformers that are large language models throughout this lesson. Some of these models are quite large, hence the name, and might take a minute or so to load. We recommend not running any other cells in the notebook while this is happening. If you haven't used Jupyter on our learning, okay, I've done it though. It is useful, not necessary to download the Jupyter notebooks in this lesson and run it in your local as you progress through this lesson, especially if you're interested in trying out heavier and more sophisticated models on your own. We will provide recommendations throughout. Hugging Face's documentation on installing the Transformers package is also quite handy for this. We highly recommend not writing any extra lines of code than what's being asked for in the notebooks, specifically code involving loading models, training, and even inference. Sometimes can be memory heavy and can cause the kernel to crash. You can always download the notebooks to your local to test out your ideas and see where your curiosity takes you. So I guess what I'll do for now is open up a collab, and if I feel so inspired, I will, do some stuff on my own. But for now, first of all, isn't that what I'm doing right now? Well, regardless, let's come back. Where am I? Let's focus. Focus. A little bit confusion. What course am I in? Intro to AI Transformers. Okay. So I guess today I want to do this. There's a lot to do. I want to do these. Tomorrow I'll focus more on going backwards and doing the preliminary, like finishing the machine learning stuff. But I just, I want to have fun. This is fun for me. So the most basic object in the Hugging Face Transformers library is the pipeline function. Run the setup cell where we've already imported the pipeline object and set up a sentiment classifier pipeline. Uncomment the line pertaining to printing the classifier object and run it to examine the output. So set up the most basic object in the Hugging Face transformers library is this pipeline function. So run the setup cell where we've already imported the pipeline object and set up a sentiment classifier pipeline. So from transformers, import pipeline, classifier equals pipeline, task equals sentiment analysis, model equals Distilbert base, uncased, fine-tuned, SST to English. So we ran that, checkpoint 1 of 2, load the pipeline. Uncomment the line pertaining to printing the classifier object and run it to examine the output. Don't forget to run the cell and save the notebook before selecting test work. Open the Jupyter. Okay, so if we print classifier, we get this place in memory. So transformers.pipelines.text classification. Text classification pipeline object at this place in memory. So let's save this and test the work. Checkpoint 2 of 2, performing sentiment analysis. We've presented some sample text to be classified using this pipeline object. Uncomment the relevant lines and press run to view the results of the sentiment analysis. Don't forget to run the cell and save the notebook before selecting test work. Open it. Okay, so example text to be classified. Uncomment the relevant lines and press run. So we have this sample text. I've been waiting to learn about transformers my whole life, and I hate this so much. That's positive. This is negative, I'm gonna guess. Nice, nice. What's interesting? Do the sentiment labels and score make sense? I think so. I'd say yes. Let's go to the next one. Behind the pipeline. Now that you've had a sneak peek into what's possible with the pipeline object, let's examine what's actually behind the pipeline. The pipeline that we've seen groups together 3 steps: pre-processing, passing the inputs through the model, post-processing. Let's quickly go over each of these. Pre-processing with the tokenizer. The first step involves converting raw text into arrays of numbers that can be processed by transformer models. This is done with the help of a tokenizer. Let's let that digest, right? So pre-processing, so the pipeline that we've seen groups together 3 steps: pre-processing, passing the inputs through the model, and post-processing. So first is pre-processing with the tokenizer. The first step involves converting raw text into arrays of numbers that can be processed by transformer models. This is done with the help of a tokenizer. Tokenizers first split inputs into words, subwords, or symbols like punctuation that are called tokens. Each token is mapped to an integer, and additional inputs that might be useful to the model are added. It is essential that the pre-processing is done exactly the same way as the model was pre-trained. This can be done by downloading this information from the model hub using the from pre-trained method from the auto-tokenizer class as follows. From transformers, import auto-tokenizer, checkpoint equals Distilbert base uncased fine-tuned SST to English, tokenizer equals auto-tokenizer.from pre-trained, checkpoint. So again, each token is mapped to an integer, and additional inputs that might be useful to the model are added. It is essential that the pre-processing is done exactly the same way as the model was pre-trained. This can be done by downloading this information from the model hub using the from pre-trained method from the auto-tokenizer class as follows. 2. Going through the model. The outputs of our tokenizer can be processed through the pre-trained model. Similar to the previous step, Hugging Face Transformers package provides an auto model class, which also has a from pre-trained method to do this. However, we don't merely want to pass our text through the transformer model. We would like it to perform a classification task. This is done by model heads, which are specific layers that tweak the transformer architecture to perform specific tasks such as question answer, sequence classification, etc. So instead of using the auto model class, we will be using auto model for sequence classification to perform sentiment analysis. From transformers, import auto model for sequence classification, checkpoint equals Distilbert base uncased fine-tuned SST to English, model equals auto model for sequence classification dot from pre-trained, checkpoint. And reading that again, so step 1 was pre-processing with a tokenizer, where our text was split into tokens, and each token is mapped to an integer, and additional inputs that might be useful to the model are added. And it's essential that pre-processing is done in the same way the model was pre-trained, which we can, this can be done by downloading the information from the model hub with from pre-trained method from the AutoTokenizer class. And from transformers import AutoTokenizer, checkpoint equals DistilBird that. Tokenizer is AutoTokenizer.free from pre-trained, and we're getting that. Step 2 is going through the model. The outputs of our tokenizer can be processed through the pre-trained model. Similar to the previous step, Hugging Face Transformers package provides an auto model class. Again, the outputs of our tokenizer can be processed through the pre-trained model. Similar to the previous step, Hugging Face Transformers package provides an auto model class, which also has a firm pre-trained method to do this. However, we don't merely want to pass our text through the transformer model. We would like it to perform a classification task. This is done by model heads, which are specific layers that tweak the transformer architecture to perform specific tasks such as question answer, sequence classification, etc. So instead of using the auto model class, we will be using auto model for sequence classification to perform sentiment analysis. And we import it so that from transformers and model equals auto model for sequence classification dot from pre-trained, and using this DistilBird. Post-processing the output, the values we get as output from our model don't necessarily make sense by themselves. Transformer models output logits, raw, unnormalized scores, outputted by the last layer of the model. They need to be passed through a softmax function that can convert this tensor output into a probability distribution of outcomes. Let's implement each of these steps now. In the setup cell in the notebook to the right, we've already imported AutoTokenizer and auto model for sequence classification from the transformers package, as well as set the model checkpoint to DistilBird base uncased fine-tuned SST2 English. So first is tokenization. So first, let's run this. Run the setup cell to import the functions and set the model checkpoint. Now, in the cell that corresponds to this checkpoint, we have loaded a tokenizer as well as an array raw inputs that contains the same two sentences we used in our previous exercise. Define a variable inputs that applies the tokenizer function on raw inputs, followed by the following arguments: padding equals true, truncation equals true, and return tensors equals pt. Print inputs to examine what the tokenized inputs to the model look like. So in order to apply the tokenizer function on raw inputs, we're going to go ahead and do inputs equals AutoTokenizer. Wait. So did we pass it? Is it like this? Honestly, not too sure. But I believe I don't think that's right. Print a variable, define a variable inputs that applies the tokenizer function on raw inputs. How do we do that? Let's find out. Inputs equals tokenizer, raw inputs, padding equals true, truncation equals true. So I thought I did it right. Did I misspell something? Why isn't printing inputs working? Is it taking all this time? Oh, okay. Cool, so passing inputs through the model. If you examine the printed outputs, you will notice that there are two arrays, input IDs and attention mask. The former refers to the tokenized inputs, and the latter shows which parts of the input are accessible to the attention layer or not. We will examine these deeper in the following exercises. And again, what is the task here? Okay, it's just a tokenizer, okay? Now, in the cell that corresponds to this checkpoint, we've already loaded the model for sequence classification in the cell below. Define a variable outputs that passes the inputs through the model as follows. Outputs equals model inputs. So this is just passing however many inputs to the model, and we print outputs dot logits dot shape. Print output dot logits oops, misspell. It's really crazy how much compute it seems to take for this. I guess maybe it's not too crazy. I wonder how many billions of parameters this Dilbert is. So torch.size 2, 2, and the tensor is this. And let's save this and test the work. This creates an object with many attributes. Print 2 of these attributes. Okay, so post-processing. The tensor outputs of the model are unnormalized numbers that are hard to draw conclusions from in their current form. To interpret their outputs, we need to convert them to probability distributions. The code for this has already been written in the cell that corresponds to this checkpoint, but has been commented out. Uncomment the relevant line and print the following to examine what they looks like. Predictions, model.config, ID to label. The former gives us the matrix that corresponds to the probability that a sentence belongs to either class, and the latter gets us the class labels for the classification. So we're going to uncomment this line, converting the outputs to probability distributions. So torch.neuralnetwork.functional.softmax outputs.logits, which is this tensor, dimension equals -1. Convert the outputs to probability distributions and print predictions. And print model.config.id2 label. So our predictions is this tensor. Notice that the numbers are different, significantly smaller, and instead of grad fn, so I'm guessing that means gradient function, I believe, add backward. Now our grad fn is softmax backward. And we have for our model.config ID to label 0, -1, positive. What can we conclude? The tensor output can be read as follows. First sentence, -0.0402, positive 0.9598. Second sentence, -0.9995, positive 0.0005, which was the exact numbers we obtained in our previous exercise. I'm a little bit confused. Revisiting pipeline. If you would like to double check the above numbers, you can rerun the following piece of code on your local. So the reason that there's this discrepancy is because they're using different sentences. It seems like there was a rounding thing here. I don't know. Did I mistype something? Model.config ID to label. Will it accept it? We have successfully reproduced 3 steps of the pipeline. Pre-processing with tokenizers, passing the inputs through the model, and post-processing. Now let's take some time to dive deeper into each of those steps. Models. The word model can be ambiguous as it's an umbrella term used to describe different related ideas in the context of transformers. Let's first distinguish between a model architecture and a model checkpoint. 1. Architecture. This is the skeleton of the model, the definition of each layer and operation within the model. BERT, GPT, and T5 are specific kinds of model architecture. 2. Checkpoint. A model checkpoint refers to the set of weights generated as a result of pre-training and fine-tuning a model architecture on specific training data. For instance, BERT base uncased was the set of weights released by Google as part of the first release of BERT. Distilbert base uncased fine-tuned SST2 English, which we've used the past couple of exercises, is a version of Distilbert base uncased that's been fine-tuned on the SST2 dataset, Stanford Sentiment Treebank corpus. Distilbert base uncased is a distilled version of BERT that's smaller and faster. The model hub in Hugging Face hosts all the model checkpoints for simple storage, discovery, and sharing. The auto model class, which we looked at in the previous exercise, is great when you want to instantiate any model from a checkpoint. When no model is specified, auto model will automatically guess the appropriate model architecture for a specified task. If we already know the kind of model we'd like to use, say BERT, as was the case in the previous exercises, we could also do the following. From transformers, import BERT config, BERT model, config equals BERT config, model equals BERT model config. We've effectively loaded the architecture of BERT and randomly initialized its weights. It is, however, fairly useless for inference at the moment as it hasn't been trained yet. Training a model from scratch is a time-consuming and computationally expensive task, so it's often best to choose a pre-trained model that is suitable for the problem we'd like to solve. Loading a transformer model that is already trained is simple. We can do this using the from pre-trained method. From transformers, import BERT model, model equals BERT model.from pre-trained, BERT base cased. This model is initialized with all the weights of the checkpoint. Additionally, the weights will be downloaded and cached, so future calls to the checkpoint won't re-download them. The model can be used directly for inference on the tasks it was trained on. For instance, if it was trained on sentiment analysis, it can be used to perform sentiment analysis on new data. Alternately, it can be fine-tuned on new data for other tasks, since we can achieve good results faster by training with pre-trained weights, i.e. fine-tuning, rather than from scratch. I'm going to go ahead and read all that again, but first, quick sip. So, models. The word model can be ambiguous, as it's an umbrella term used to describe different related ideas in the context of transformers. Let's first distinguish between a model architecture and a model checkpoint. 1. Architecture. This is the skeleton of the model, the definition of each layer and operation within the model. BERT, GPT, and T5 are specific kinds of model architecture. 2. Checkpoint. A model checkpoint refers to the set of weights generated as a result of pre-training and fine-tuning a model architecture on specific training data. For instance, BERT base uncased was the set of weights released by Google as part of the first release of BERT. Distilbert base uncased fine-tuned SST2 English, which we've used the past couple of exercises, is a version of Distilbert base uncased that's been fine-tuned on the Stanford Sentiment Treebank corpus. Got you. Distilbert base uncased is a distilled version of BERT that's smaller and faster. The model hub in Hugging Face hosts all the model checkpoints for simple storage, discovery, and sharing. The auto model class, which we looked at in the previous exercise, is great when you want to instantiate any model from a checkpoint. When no model is specified, auto model will automatically guess the appropriate model architecture for a specified task. If we already know the kind of model we like to use, say BERT, as was the case in the previous exercises, we could also do the following. From transformers, import BERT config, BERT model, config equals BERT config, model equals BERT model config. We've effectively loaded the architecture of BERT and randomly initialized its weights. It is, however, fairly useless for inference at the moment as it hasn't been trained yet. Training a model from scratch is a time-consuming and computationally expensive task, so it's often best to choose a pre-trained model that is suitable for the problem we'd like to solve. Loading a transformer model that is already trained is simple. We can do this using the from pre-trained method. From transformers, import BERT model, model equals BERT model.from pre-trained, BERT base cased. This model is initialized with all the weights of the checkpoint. Additionally, the weights will be downloaded and cached, so future calls to the checkpoint won't re-download them. The model can be used directly for inference tasks it was trained on. For instance, if it was trained on sentiment analysis, it can be used to perform sentiment analysis on new data. Alternately, It can be fine-tuned on new data for other tasks, since we can achieve good results faster by training with pre-trained weights, i.e. fine-tuning, rather than from scratch. 1. Model config. Run the setup cell to import the relevant libraries in the cell corresponding to this checkpoint, print config to see what it looks like. So we import from transformers, import BERT config, BERT model, and auto tokenizer. So we did config equals BERT config, and we'll do print config. So BERT config, attention probs, dropout prob, classifier dropout, hidden act, hidden dropout prob, hidden size, initializer range, intermediate size, layer norm EPS, max position embeddings, model type, num attention heads, num hidden layers, pad token ID, position embedding type, transformers version, type vocab size, use cache, vocab size. Cool. Building the model from config. Print model to examine what a randomly instantiated model looks like. So BERT model, embeddings, BERT embeddings, word embeddings, embedding 30,522, 768, padding IDX equals 0, position embeddings, embedding 512, 768, token type embeddings, embedding 2, 768, layer norm, a bunch of stuff. So these are the embeddings information. This is BERT embeddings. For the encoder, it's using BERT encoder, which is this information with this layer module list. So attention is BERT attention self, BERT self attention, query linear in features 768, out features 768, bias equals true, key linear in features 768, out features 768. So value dropout is p equals 0.1, in place equals false, and then the output is BERT self output, dense linear in features 768, out features 768, bias true, layer norm, dropout, intermediate, BERT intermediate, dense, linear, intermediate act function, JLU activation, output, BERT output, dense, linear, in features 3072, out features 768, bias equals true, layer norm, dropout, and then pooler, BERT pooler, dense, linear, in features, out features, bias, activation, tan-h. So cool. Building a model from config, so let's test that. And then checkpoint 3, tokenizers from model checkpoint. Create a tokenizer. Tokenizer will with DistilBERT. Okay, create a tokenizer with DistilBERT based uncased fine-tuned SST2 English as the model checkpoint and default arguments otherwise. Do not set any other arguments. We will get to the arguments like padding, truncation, etc. soon. Tokenize the sample text provided and be sure to print it. So checkpoint equals this, sample text equals BERT is an encoder only transformer. To create a tokenizer called tokenizer, we're going to do tokenizer. Is it BERT model dot, how you do it again? So it would be BERT model config. So no, this is already our model. In order to create a tokenizer from this model, we do model and we pass it this checkpoint. And yeah. So it's just the model. We pass it the checkpoint. And then we can call it, we can do tokenizer sample text. And we can print it, I believe. No. String indices must be integers. That's the right way to do it. I see tokenizer auto tokenizer. Recall that to load a tokenizer from a checkpoint, We use the from pretrained method. So auto tokenizer dot from pretrained checkpoint. This is our tokenized sample text. Looking good. Want to know more about BERT? Recall that there are 3 types of transformer models based on their architecture, i.e., whether they're encoder only, decoder only, or encoder decoder models. BERT is an encoder only transformer model, and it stands for bidirectional encoder representations from transformers. Attention layers in BERT have access to all the words in a sentence, making the BERT class of models great at tasks that involve understanding an entire sentence, such as sentence classification. The original BERT model was proposed in 2018 and had 340 million parameters. We've been using a much smaller model, DistilBERT based uncased fine-tuned SST2 English. We're going to learn more about this model in the upcoming exercises. Great. Model cards. We can see how there's a lot of information to consider while choosing a model. Parameter size, details about the training data, and task-specific training are some of the important things to consider. Many other details, such as when, why, and by whom a model was built, are crucial to catalog as well for transparency and reproducibility reasons. Model cards are designed exactly for these purposes. What are model cards? Model cards are files that accompany the models and provide handy information. Under the hood, they are simple markdown files with additional metadata. Model cards are essential for discoverability, reproducibility, and sharing. They can be found as the readme.md file in any model repo. Mitchell 2018 provided a detailed template on how to create model cards, which I'll go ahead and save that actually. In the image to the right, we have a screenshot of the model card for the model we've been working with so far, DistilBERT based uncased fine-tuned SST2 English. You can find the entire model card and associated files in Hugging Face's Model Hub. We've already noted that this is a version of DistilBERT based uncased that has been fine-tuned on the SST2 dataset for the Stanford Sentiment Treebank corpus to perform sentiment analysis. Scrolling down the model card page further, one can find detailed information about how to best use the model, its misuse and out-of-scope use, risks and biases, and detailed information about training as well. The model card template is available in Markdown format in GitHub at this link. My downloads, NLP, model card template, going in NLP, get in there, cool. So anyway, in general, the model card should describe technical details about the model, its intended uses and potential limitations, including biases and ethical considerations, the training parameters and experimental info, details about the datasets used to train the model, evaluation results about the model's performance. Model cards on the hub have 2 key parts with overlapping information, text descriptions, and metadata. We've already seen what is included in the text descriptions. Metadata can be and is often added to the model card to support discovery and easier use. Some examples of this include allowing users to filter models, add Hugging Face models, displaying the model's license. Adding datasets to the metadata will add a message titled datasets used to train to the model card and link to relevant datasets if they're available on the hub. Tokenizers. Transformer models can only process numbers, so any data type, text, image, audio, etc., that they work with needs to first be pre-processed and converted to numbers. Tokenizers are here to help with this task. We've seen how auto-tokenizer can be used already. Let's now break down the different processes contained within tokenization. 1. Tokenization. The first task is to break up text, including symbols and punctuation, into meaningful representations before turning them into math. The smallest unit of text that is turned into a number is known as a token. Depending on the language task to be done, different pieces of text can function as tokens: characters, words, subwords, groups of words, /subwords, etc. Many language models have their own special types of tokenization methods: byte level BPE, as used in GPT-2, word piece, as used in BERT, sentence piece or unigram, as used in several multi-language models. Since we'll be working with the BERT architecture, the tokenizer that auto-tokenizer will select is word piece. The vocabulary of a tokenizer is determined during the training process, and we're not going to go into how it's done in detail. You can check out this link if you're interested. The important things to know are: word piece is a subword tokenizer that starts from a small vocabulary that includes the alphabet and a few special tokens. It identifies subwords by adding a prefix, ###. Each word is initially split by adding that prefix to all the characters inside the word. So, for instance, word gets split into this: list W, comma, ##O, comma, ##R, comma, ##D. These subwords are merged depending on a weighted frequency of their co-occurrence as well as separate occurrences. We will see what this looks like in our second checkpoint. So that didn't really fully get in my brain, so I'm going to reread it from the top. So not quite from the top. 1. Tokenization. The first task is to break up text, including symbols and punctuation, into meaningful representations before turning them into math. The smallest unit of text that is turned into a number is known as a token. Depending on the language task to be done, different pieces of text can function as tokens: characters, words, subwords, groups of words, /subwords, etc. Many language models have their own special types of tokenization methods: byte level BPE, as used in GPT-2, word piece, as used in BERT, sentence piece or unigram, as used in several multilingual models. Since we'll be working with the BERT architecture, the tokenizer that auto-tokenizer will select is word piece. The vocabulary of a tokenizer is determined during the training process, and we're not going to go into how it's done in detail. You can check out this link if you're interested. What is this link? Okay, maybe I'm interested, maybe later though. The important things to know are: word piece is a subword tokenizer that starts from a small vocabulary that includes the alphabet and a few special tokens. Again, word piece is a subword tokenizer that starts from a small vocabulary that includes the alphabet and a few special tokens. It identifies subwords by adding a prefix, ##. Each word is initially split by adding that prefix to all the characters inside the word. So for instance, word gets split like so. These subwords are merged depending on a weighted frequency of their co-occurrence as well as separate occurrences. We will see what this looks like in our second checkpoint. 2. Encoding. Tokenizers in the transformers package do more than tokenizing. They translate text to numbers through a process known as encoding. This involves tokenization as well as conversion of tokens into integers known as input IDs. These input IDs form a tensor, which is essentially a large array of numbers. The tokenizer does this by referencing a vocabulary, the set of tokens that a model has been trained on. Since transformer models have distinct methods for tokenization, as well as distinct vocabularies, it's essential that we load the tokenizers relevant to the model we're using. This is why auto-tokenizer allows us to load from pre-trained, so we can call the same model that we intend to use for inference as well. 3. Decoding. Decoding is the reverse process of converting the input IDs back to text. The decode method allows us to do that. Decoded string equals tokenizer.decode 7993 170 11303 1200 2443 and so on. Print decoded string. So again, decoding is the reverse process of converting the input IDs back to text. The decode method allows us to do that. So we do tokenizer.decode, decoded string, and we print it, and the output is: using a transformer network is simple. Was that our input text? Okay. Just to, really get this in my brain. So tokenizer references the vocabulary. The input IDs form a tensor. Okay. Since transformer models have distinct methods for tokenization as well as distinct vocabularies, it's essential that we load the tokenizers relevant to the model we're using. This is why auto tokenizer allows us to load from pre-trained, so we can call the same model that we intend to use for inference as well. Batching, padding, and truncation. If we just tried to input the tokenized text into a model, it would fail. This is because models expect multiple sequences by default. Batching is the act of sending multiple Batching is the act of sending multiple sentences through the model all at once. If you only have one sentence, you can just build a batch with a single sequence. When we do have multiple sequences, we run into a different issue. They can be different sizes, like in lengths of sentences, for instance. This is where padding comes in. In language models, padding makes sure all our sentences have the same length by adding a special word called the padding token to the sentences with fewer values. Sometimes we might have a few outlier sentences that are extraordinarily long, and it might not make sense to pad all sequences to that size. Here, truncation comes in handy. One can truncate sequences by specifying the max sequence length parameter. Sequence equals sequence up to the max sequence length. A note about attention masks. Recall that different transformer types mask tokens differently, and thus the tokens that their attention layers have access to vary. Attention masks are tensors with the exact same shape as the input ID's tensor, filled with zeros and ones. Ones indicate the corresponding tokens should be attended to, and zeros indicate the corresponding tokens should not be attended to, i.e., they should be ignored by the attention layers of the model. Let's try out all of these now. So first, breaking text into tokens. The simplest way to break text into words is using Python's split function. For a given sequence, this would look like split sequence equals sequence.split. For the sequence given in the cell corresponding to this checkpoint, create a variable tokenized array that represents the result of applying split on the sequence, sample sentence, print the output to see what it looks like. So first, we'll run from transformers, import auto tokenizer, and create a variable tokenized array that represents the result of applying split on the sequence. So sample sentence dot split, and then we want to print the output. Brevity is the soul of wit. Next up, we'll save this and test the work. How would the model we've been working with, i.e. Distilbert-based uncased fine-tuned SST2 English, split this sentence? To examine this, create a tokenizer for the model checkpoint. So tokenizer equals cool. Use the .tokenize method on the sample sentence. So use the .tokenize method on the sample sentence to obtain tokenized array word piece, the set of tokens generated by the model, and print it. So tokenized array word piece equals tokenized array dot tokenized. Oh, I forgot to print it. Okay. So we see BR double hashtag EV double hashtag ITI is the soul of wit. period. Encoding. Now, so apply the tokenizer to the given sequence. Save the tokenized results as input tokens. So input tokens equals tokenizer, tokenize sequence. Print it to examine what it looks like. So save it, test the work. To decode the input IDs, tokenizer.tokenize sequence, print input tokens, What's the discrepancy? Oh. So this was the WordPiece tokenizer. This is encoding. Apply tokenizer to the given sequence. Save the tokenized result as input tokens and print it to examine what it looks like. Don't forget to run the cell and save the notebook before selecting test work. So save it, test work. To decode the input IDs from the tokenized inputs, input tokens need to be passed through the .decode function. Store the decoded output as decoded sequence and print it. So decoded sequence equals I think that's right. Uh-oh. Will it restart automatically? Damn. Don't do me like this. Don't do me like that. Okay. But this was a lot of work. That wasn't really that much work. I'm just being a baby. So anyway, create a variable tokenized array that represents the result of applying split on the sequence sample sentence. Nice. And then create a tokenizer for the model checkpoint equals auto tokenizer dot from pre-trained checkpoint. Use the dot tokenize method on the sample sentence. So tokenized array word piece equals tokenizer dot tokenize sample sentence, and then print tokenized array word piece auto. Damn. Cool. Apply the tokenizer to the given sequence. Save the tokenized result as input tokens. To decode the input IDs from the tokenized inputs, input tokens need to be passed through the decode function. Store the decoded output as decoded sequence equals tokenizer dot decode input tokens printed. Uh-oh. I've been waiting for a Hugging Face course my whole life. Checkpoint 5.7 batching. We've created an array sequences with 2 sentences. Print the tokenized output for this batch. So last time when we had a sequence, to do the tokenizer, so we already have our tokenizer. We can just do tokenizer.tokenize. So we've already noted transformer models expect model inputs to be in batches. Created an array sequences with 2 sentences. Print the tokenized output for this batch. What am I missing? Model inputs batched equals tokenizer sequences. Print model inputs batched. Oh, I see. Padding. Create and print model inputs padded 3 with the following. So padding can be done with a few different objectives. In the cell corresponding to this checkpoint, we've provided 2 examples of padding and tokenization. The first example, where the argument is padding equals longest, will pad the sequence up to the maximum sequence length in the given batch of sequences. The second example, where the argument is padding equals max length, restricts the maximum length allowed to that of the model. In case of BERT, this is 512. If we wanted to specify our own custom length, we can use a separate argument, max length, and set it to the number of our choice. Create model inputs padded 3 with the following arguments to the tokenizer. Padding equals max length equals 8. Print model inputs padded 3 to examine it. So create and print model inputs padded 3. With the following arguments to the tokenizer. So sequences padding equals max length equals 8. Don't forget to run the cell and save the notebook before selecting test work. Maybe we weren't supposed to pass it sequences. Seems like we were. But we'll see. So padding will pad the sequences up to the maximum sequence length. Model inputs padded 1 equals tokenizer sequences. Padding equals longest. This will pad the sequences up to the model max length. 512 for BERT or DistilBERT. Model inputs padded 2 equals tokenizer sequences. Padding equals max length. Pad the sequences up to the specified max length. Model inputs padded 3. Tokenizer sequences padding equals max length. Max length equals 8. So let's go ahead and steal this. See if we can notice any differences when we paste it other than the 3. Don't really notice differences. So I'm still going to change it to 3. See if it works. Still doesn't work, so check out the solution. Model inputs padded 3, tokenizer. Oh, I just didn't print it. Create and print. So let me check out, I want to check out all of them. So this first one, padding equals the longest, input IDs, and the attention mask. For just max length, this is crazy stupid long. And then for max length, preset to 8, we get this. Interesting. So I'm just going to read this. Padding can be done with a few different objectives. In the cell corresponding to this checkpoint, we've provided 2 examples of padding and tokenization. The first example, where the argument is padding equals longest, will pad the sequence up to the maximum sequence length in the given batch of sequences. The second example, where the argument is padding equals max length, restricts the maximum length allowed to that of the model. In case of BERT, this is 512. If we wanted to specify our own custom length, we can use a separate argument, max length, and set it to the number of our choice. Create model inputs padded 3 with the following arguments to the tokenizer, and then print it to examine it. Truncation. To truncate sequences, we can use the argument truncation. When set to true, as is the case with the example provided in the cell corresponding to this checkpoint, sentences that are longer than the default size specified by the model, 512 tokens in the case of BERT, will be truncated. To create custom length outputs, create model inputs truncated 2, which specifies an additional argument called max length, and set it to 8. Print model inputs truncated 2 to examine it. So again, to truncate sequences, we can use the argument truncation. When set to true, as is the case with the example provided in the cell corresponding to this checkpoint, sentences that are longer than the default size specified by the model, which is 512 tokens in the case of BERT, will be truncated. To create custom length outputs, create model inputs truncated 2, which specifies an additional argument called max length, set as 8. Print model inputs truncated 2 to examine it. So similar to the given model inputs truncated 1, create a truncated model inputs truncated 2. Which specifies an additional argument, max length, set it to 8. Print model inputs truncated 2 to examine it. Sequences, I've been waiting for a Hugging Face course my whole life, so have I. We can see, compared to model inputs truncated 1, this one is lesser. Max length of 0, 1, 2, 3, 4, 5, 6, 7, so max length of 8 makes sense. Transformer model types. The 3 basic transformer types based on their architecture are autoregressive GPT-like models that have a decoder-only architecture, autoencoding BERT-like models that have an encoder-only architecture, sequence-to-sequence BART T5-like models that have an encoder-decoder architecture. Autoencoding transformer models specialize in tasks requiring contextual understanding, such as sentiment analysis, named entity recognition, which is the process of identifying and classifying specific people, places, or things, and extractive question answering. We've worked with a version of BERT in the first 5 exercises of this lesson and looked at a couple of different methods of doing model inference. In the coming exercise, we will look at sequence-to-sequence models. These are encoder-decoder models that specialize in tasks involving the transformation of one sequence of data into another, such as translation, text summarization, and generative question answering. The last couple of exercises of this lesson will focus on autoregressive or decoder-only models. we will work on GPT-2 and examine different strategies for text generation. So again, autoregressive transformer architecture. Hold on, let me just. Autoregressive transformer architecture, decoder only. Suitable language tasks are text generation. Auto-encoding transformer architecture, encoder only. Suitable tasks are sentence classification and named entity recognition. Sequence-to-sequence transformer architecture is encoder-decoder. Suitable language tasks are summarization and translation. Cool. Encoder-decoder models, summarization with T5. We're now going to do some model inference with encoder-decoder models and apply many of the things we've learned in the previous exercises. Encoder-decoder models use both the encoder and decoder parts of a transformer and are often referred to as sequence-to-sequence models. Recall that the attention layers of the encoder can access all the words in a given sentence, whereas the attention layers of the decoder can only access the words positioned before a given word in the input. Again, the attention layers, the attention layers of the encoder can access all the words in a given sentence, whereas the attention layers of the decoder can only access the words positioned before a given word in the input. This means that sequence-to-sequence models are great at generating new sequences like a decoder-only model, but with a focus on understanding the context within the input sequence like in an encoder-only model. Thus, the tasks that they are most appropriate for are summarization, translation, and generative question answering. BART, T5, and Marion are some examples of encoder-decoder models. In this exercise, we'll be using a version of T5. T5, or text-to-text transfer transformer, was released in 2019 by Google. It's a ridiculous amount of T's. It is pre-trained in a rather unique way. Sentences are first corrupted by replacing about 15% of the tokens and replacing them with random placeholder tokens. This is fed as an input to the encoder. The placeholder tokens are masked, and the decoder is trained to predict them while using the original uncorrupted tokens as the target. This makes T5 very well suited to tasks that involve generating sentences based on contextual understanding of the input sequences, such as summarization. We're going to put together all we've learned in the previous exercises to perform a summarization task using a smaller version of T5, Google Flan T5 Small. You can find the model card for that model there. Uncomment and run the lines pertaining to loading the model in tokenizer. So from transformers, import auto model for sequence-to-sequence LM. Auto tokenizer, import numpy as MP. Our checkpoint is Google Flan T5 Small. The text to be summarized is all of that. This is a dirty secret about the carbon footprint, huh? AI startup Hugging Face believes it's come up with a new, better way to calculate that more precisely by estimating emissions produced during the model's whole life cycle rather than just during training. It could be a step towards more realistic data from tech companies about the carbon footprint of their AI products at a time when experts are calling for the sector to do a better job of evaluating AI's environmental impact. Hugging Face's work is published in a non-peer-reviewed paper. To test its new approach, Hugging Face estimated the overall emissions for its own large language model, Bloom, which was launched earlier this year. It was a process that involved adding up lots of different numbers: the amount of energy used to train the model on a supercomputer, the energy needed to manufacture the supercomputer's hardware and maintain its computing infrastructure, and the energy used to run Bloom once it had been deployed. The researchers calculated that final part using a software tool called Code Carbon, which tracked the carbon dioxide emissions Bloom was producing in real time over a period of 18 days. Hugging Face estimated that Bloom's training led to 25 metric tons of carbon dioxide emissions, but the researchers found that figure doubled when they took into account the emissions produced by the manufacturing of the computer equipment used for training, the broader computing infrastructure, and the energy required to actually run Bloom once it was trained. So the training led to 25 metric tons of carbon dioxide emissions. Hard to really understand if that's even a big or a small number in the grand scheme of emissions, but it sounds big, and it's interesting to think how that number will grow and is growing as time goes on. So anyway, uncommented and run the lines pertaining to loading the model in tokenizer. So tokenizer equals autotokenizer.fromPretrained checkpoint, and model, make sure you don't rush this cell more than once or else the kernel might crash. Oh, don't run it more than once. Model equals auto model for sequence-to-sequence LM. dot from pre-trained checkpoint. Uncomment the run. Okay, so we're uncommenting them. We want to create input tokens for the summarization model, but here we only want the input IDs. Real quick, I'm just going to save this and test the work. So we want to create input tokens for the summarization model, but here we only want the input IDs as a tensor and are not interested in the intention mask. To do this, create tokens input. So using the tokenizer with the .encode method that has the following arguments. Once you've created tokens input, print its shape using np.shape. Torch.size 1369. Checkpoint 33 summarization task. Uncomment the line that generates the summary tokens. Create a variable summary that uses the decode functionality. So of the tokenizer. With the following arguments. Print summary to examine the output. Hugging face is a new, better way to estimate. Oh, because it's summarizing it, right? That's cool. Hugging face is a new, better way to estimate emissions produced during the model's whole life cycle rather than training. It can be a step toward more realistic data from tech companies about the carbon footprint of their AI products at a time when experts are calling for the sector to do a better job of evaluating AI's environmental impact. Hugging Face estimates the overall emissions for its own large language model Bloom, which was launched earlier this year. It makes sense. I wish they included the metrics though. You might already be able to tell that the summary is not great. Summary misunderstands what Hugging Face is, but manages to get a few key points right. For a better summary, you can download the same notebook and attempt a heavier and better model like Flan T5 Base or BART Large. Let's try it. Why not? How do I download it? Let's download this as IPYNB. Let's go over to my collaboratory file, open a notebook, upload a notebook, browse, downloads, right there. Let's connect. Let's connect to a big boy GPU. How much does this one cost again? A bunch of compute resources. It's because I'm paying for this and I keep forgetting to not be paying for it. It's taking a long time to connect. Excuse me. It's starting to become less, more hassle than it's worth. Come on. Do the thing. Okay. And I'm on the GPU? Sorry. Okay, cool. So, oh wait, I don't want that. Why is it connecting again? This is annoying. Alright, here's what I'm gonna do. Am I on the GPU or am I not? I am, okay? So now what I'm gonna do is, where am I? Bart large. We'll try flan T5 base. Where am I going? Where am I going? Right here. I guess I could just do this. Still doesn't give me the numbers. I don't know if this is gonna, I feel like, how long is this gonna take? Maybe that's not the right thing. Regardless, whatever. I get it. Let's go. Let's keep. Let me real quick though. Change runtime type. Let's close this. And back to where I ought to be without the distractions. So save this, test the work. Next, decoder basics with GPT-2. The key difference between encoders and decoders in transformer architectures is the decoder's ability to perform autoregressive tasks. Autoregression refers to the model's ability to feed output at one time step back into the model as input in subsequent time steps. Consider a decoder-only text generation model like GPT-2. When prompted with text like the quick brown fox, assume GPT-2 generates the token jumps. To finish the sentence, GPT-2 must append this output to the end of its input sequence and generate a fresh output with the new prompt, the quick brown fox jumps. It then continues repeating this process until it reaches an end of sequence token that tells it to end the output. This process of adding output at time step t to the input at time step t plus 1 is what we mean by autoregressive. Via this step-by-step autoregressive process, models like GPT-4 generate long strings of helpful text for users worldwide. We'll give text generation a try via the ultra-lightweight distilled GPT-2 model from Hugging Face. Distilled GPT-2 is less than 200 megabytes smaller, or is about 200 megabytes smaller than GPT-2 and has around 50 million fewer parameters. Note, if you'd like an extra challenge, try running the code in this exercise in notebook locally on your own device using the full GPT-2 model instead. Simply substitute GPT-2 for distilled GPT-2 in the call to from pre-trained at the start. So using the GPT tokenizer, run the setup cells to instantiate the model in tokenizer. In the cell corresponding to this checkpoint, pass the new text we've defined to the tokenizer via the tokenizer.encode method. Include the argument return tensors equals pt while performing tokenization so that our model inputs are PyTorch tensors. Assign the returned value to a variable named pt tokens and print the resulting tensors to the console. So tokenizer equals GPT-2 tokenizer.from pretrained distill GPT-2 model equals GPT-2 lm head model.from pretrained distill GPT-2. Our text is let's turn the string into a PyTorch tensor of tokens, and pt tokens equals tokenizer.encode text turn tensors equals pt, and we'll print pt tokens. Decoding the tokens. Turning tokens back into a full text string again is quite simple. Just pass your tokens to the tokenizer.decode method. In the cell corresponding to this checkpoint, we've created a list with some tokens containing a secret message. Decode the resulting list tokens. Store the result in decoded tokens. If you're reading this, you decoded me. All right, time. So fun with text generation. Uncomment the lines corresponding to this checkpoint and test the model's text generation capabilities with a few prompts of your own. So, all right, time to generate some text with the model. A few notes on the parameters we'll set. As mentioned earlier, the model will read in a PyTorch tensor made of tokens. We'll specify the parameters do sample equals true, num beams equals 1. We'll see what both mean in the following exercise. The pad token ID parameter is used to avoid a warning. It tells the model to use the end of sequence token to fill in the white space in each sequence. Try it out below. Feel free to experiment with different prompts to get a feel for how this particular model behaves. Once you're done, don't forget to hit test work to move to the next checkpoint. So prompt, hello, my name is, inputs equals tokenizer.encode the prompt, and return tensors pt, output equals model.generate, inputs max length equals 75, num beams equals 1, do sample equals true, pad token ID tokenizer.eos token ID, and print tokenizer.decode output 0. So again, model read in a PyTorch tensor made of tokens. That's what this return tensors pt is doing in this tokenizer.encode method. We'll specify the parameters do sample equals true and num beams equals 1. We'll see what both mean in the following exercise. The pad token ID parameter is used to avoid a warning. It tells the model to use the end of sequence token to fill in the white space in each sequence. Try it out below. So hello, my name is, let's just see what it does. Hello, my name is Ravi. The new script uses a C compiler. This lets us simplify the initialization of the code as well as simplify the initialization. We'll create an example code for the library. We'll be using the following functions. For instance, we need to have a class. What is it even saying here? To say something for this to be useful, I'm a physicist. I have now graduated from University of Colorado. Dang, this thing sucks. Anyway, save it. I mean, it's amazing, but you know, compared to GPT-4, it's like crazy. So next, we'll experiment with changing the model's temperature. Warmer, higher values reduce the predictability of the model and can generate more creative outputs, while cooler, lower values instruct the model to select only the most likely completions, making its output more predictable. Call the generate text function below twice on the same prompt with different temperatures. The second argument of your generate text function should be temperature. So call generate text with our predefined prompt. Set the temperature equal to 1.2. Then store the result in a variable named high temp. And call generate text. So it's going to be low temp. With our predefined prompt and set the temperature equal to 0.3. Print both high temp and low temp to the console, each on their own lines. Note we set seed in the second line of the cell. That's to ensure reproducible outputs. So the text generation we will see will be the same generation you see when running the code. Setting seed can be helpful when you want predictable outputs in your generations. Okay, cool. So artificial intelligence is, and in here we get is in the making. These are just some of the tools Apple used to design software. The toolkit has already been deployed on a lot of blah, blah, blah. Artificial intelligence is a field of study that has been exploring the potential of artificial intelligence. A new study published in the journal Nature Communications suggests that artificial intelligence can promise a new way to exploit potential. Dang, that's that's funny. So save it. Test the work. In high temp, did you pass prompt and 1.5 to generate text? I thought I did. Sorry, did I say 1.5? It's 1.2. Is it? What's the discrepancy? Oh no, don't do that. Don't do that. What's the issue here? Oh, it's because I did temperature equals. Are you serious? Whatever. Token selection strategies of the GPT-2. Now we'll explore some of the strategies text-generating decoder models employ to select their next token. Before getting started, run the code cell under Setup to import and instantiate our model and its tokenizer, same as last time. This might take a minute or so and will be done by the time you get done with the narrative. So from transformers, import GPT-2 LM head model, GPT-2 tokenizer. Tokenizer equals GPT-2 tokenizer from pre-trained, distilled GPT-2. Model equals GPT-2 LM head model from pre-trained, distilled GPT-2. From transformers, import set seed, set the seed. So greedy search. In greedy search, the model chooses the likeliest next token at each step in the sequence. In the diagram above, the numbers on each line represent the model's prediction of that token's probability of being next in the sequence. In the first step, the model chooses dog because it's most likely. In the second step, it chooses walked because it's most likely. Greedy search is the default in distill GPT-2. This approach typically leaves much to be desired, as we will see shortly. Note in the diagram above how very likely tokens hidden behind less likely ones, such as swims, are obscured in this approach. Our next strategy, beam search, tries to mitigate this approach. So beam search evaluates several paths, beams, deeper into the sequence and calculates their total probability before choosing the one with the highest sum. In the diagram above, each beam is a dashed red line. The beam with the highest probability is fish swims. There are 3 beams displayed, but that value can be defined by the user via the numBeams parameter passed to model.generate, n-gram penalty. While beam search can potentially find better sequences than greedy search and thus generate better outputs, it can easily get stuck in a loop of repeating itself like in greedy search. One technique to prevent this repetition is via setting n-gram penalties. An n-gram is just a sequence of tokens of length n. Setting an n-gram penalty means preventing any sequence of length n from repeating itself throughout the output. Sampling. However, as you can imagine, preventing any repetitions of n length can be too restrictive for many use cases. Imagine a sports article about women's soccer that's only allowed to say women's soccer one time. Another problem with our current configuration is that the text is not quite random enough. As it turns out, human text is a lot more random. To make our text more natural, we can tell GPT-2 to select the next token at random from among a handful of likely candidates. Let's try out all these strategies with distilled GPT-2. So greedy search. In greedy search, the model chooses the likeliest next token at each step in the sequence. In the diagram shown, the numbers on each line represent the model's understanding of that token's probability of being next in the sequence. Check out the output of greedy search by uncommenting and executing the code cell corresponding to this checkpoint. So prompt equals the capital of France is inputs tokenizer.encode prompt return tensors pt greedy outputs equals model.generate input max length 50 pad token id equals tokenizer.eos token id. Don't mind the pad token id bit here, it's just included to avoid a warning message. And we print tokenizer.decode greedy outputs. This approach certainly leaves much to be desired, as the capital of France is the capital of the French Republic. The capital of France is the capital of the French Republic. Jesus. So, yeah, much to be desired. Note in the diagram above how very likely tokens, peace be upon him, hidden behind less likely ones such as swims are obscured in this approach. Our next strategy, beam search, tries to mitigate this problem. Checkpoint 2 for beam search. So it evaluates several paths real quick. Let me just save this and test the work. Beam search, modify the call to model generate. So again, let me just read this. It evaluates several past beams further into the sequence and calculates the total probability. Oh yeah, I've already read that kind of. So modify the call model generate such that it performs beam search using 5 beams. So set number of beams. Maybe I should read this. So it evaluates several past beams further into the sequence and calculates their total probability before choosing the one with the highest sum. In the diagram above, each beam is a dashed red line. The beam with the highest probability is my fish swims. There are 3 beams displayed, but that value can be defined by the user via numBeams parameter passed to model.generate. Let's try it. Modify the call to model.generate below such that it performs beam search using 5 beams. Don't touch anything else. So numBeams equals 5. The capital of France is the capital of France. It is the capital of France. It is the capital of France. It is the capital of France. Well, beam search can potentially find better sequences and thus generate better outputs than greedy search. As you can see above, it struggles with the same problem greedy search did in our earlier example. It can easily get stuck in a loop of repeating itself. N-gram penalty. So let me save this and test it. So one technique to prevent this repetition is via setting n-gram penalties. And n-gram is just a sequence of tokens of length n. Setting an n-gram penalty means preventing any sequence of length n from repeating itself over the course of the output. We set the n-gram penalty by passing our desired size of n via the argument no repeat n-gram size in the generate method. Set that value to 2 inside the model generate call and see how it changes the output below. So capital of France is home to the world's second largest economy, according to a new report by the International Monetary Fund (IMF) and the World Bank Organization. The report, which is based on data from okay, that's an improvement. However, as you can imagine, preventing any repetitions of n length can be too restrictive for a variety of uses. And yeah, so sampling. Another problem with our current configuration, just test it, is that the text is not quite random enough. As it turns out, human text is a lot more random. To make our text more natural, let's tell GPT-2 to select the next token at random from among a handful of likely candidates. We'll do so by setting doSample to true. To improve its performance, we'll also turn down the temperature some to prevent the least likely outputs, as they're quite zany. We'll also instruct the model to choose from among the top 5 most likely completions, top K. To attempt more natural human text, set the following parameters in the model.generate function. Set doSample to true. Set temperature to 0.6. Set top K to 50. Then run the cell. Capital France is home to a number of top luxury brands. The world's largest luxury brand is expected to introduce. Okay, as you can see, it doesn't make the most sense. Its first new luxury home in the Americas, but we've succeeded in generating much more natural text than we started with at the beginning. I guess that's true. Cool. Save it. Test the work. Next, summary. Nice work. In this lesson, you've learned a broad overview of the different aspects of the Hugging Face Transformers package. Specifically, you've learned how to use pipeline to perform model inference, perform tokenization and pre-processing to prep model inputs, find and interpret model cards, choose transformer models for different language tasks, use an encoder-only model like BERT for sentiment analysis, use an encoder-decoder model like T5 for summarization, use a decoder-only model like GPT-2 for text generation, implement different token selection and search strategies for text generation using transformers. You're now set to explore more transformer models on your own. Which of the following statements about accessing transformer models through Hugging Face is false? Every model architecture corresponds to exactly one model checkpoint. I think that might be true, but I'm not sure. The model hub in Hugging Face hosts all the model checkpoints for simple storage. That's true. The from pre-trained method can be used to access both models and tokenizers. That's true. Loading a model architecture without specifying a checkpoint will initialize the model with random rate. So that's true. So this is false. That's right. The statement is incorrect. Many model checkpoints can have the same underlying model architecture. For example, BERT-based uncased and distilled BERT-based uncased are 2 checkpoints with the same underlying BERT architecture. When a decoder model projects several tokens further into the potential output and chooses the most probable multi-token sequence from among several candidates, the search strategy used is known as beam search. Which of the following tasks cannot be performed by the pipeline object in Hugging Face's transformers package? So pipeline can be used for pre-training the model, can be used for post-processing model outputs, tokenization, choosing model heads for specific tasks. Damn it, pre-train the model. I should have known that. Which of the following information should be present in a model card? The intended uses of the model and possible misuses or out-of-scope uses, potential biases, limitations, status use, all of them. Fill in the blanks in the following paragraph about decoder models. Decoder models employ various strategies in next token generation, which can be adjusted by the user. These include n-gram something, which prevent tokens sequences of n-gram length from repeating. I think it's n-gram penalties. Something, which chooses the next token at random from among a collection of likely next tokens. Temperature, which adjusts the predictability of the randomly selected next token, with something temperatures producing less predictable output. So higher temperatures produce less predictable output. Fill in the blanks in the following piece of code implementing a summarization task. So from transformers, import auto model for sequence to sequence LM, auto tokenizer, checkpoint equals for sequence to sequence, believe flying, tokenizer equals auto tokenizer dot from pre-trained checkpoint, model equals this, text file is Pride and Prejudice, text equals text file dot read, tokens input equals tokenizer dot encode, something plus text, summarize plus text, max length equals 512, summary IDs equals model dot generate, tokens input, so that's right. Fill in the code in the following code snippet that implements sentiment analysis with the most appropriate answer among the choices. Import torch from transformers, import auto tokenizer, auto model for sequence classification, checkpoint equals Distilbert base uncased fine-tuned SSD English, tokenizer equals auto tokenizer dot from pre-trained checkpoint, model equals something dot free auto model for sequence classification dot from pre-trained checkpoint, sequences, but waiting this, tokens equals tokenizer, output equals model, all tokens. Yes, sir. When using auto tokenizer to tokenize sequences, we can truncate sequences that are longer than a specified custom upper limit as follows. Model inputs truncated equals tokenizer sequences, bunch of x's equals 42, truncation equals true, 40, true. What is the argument that should take the places of that x's in the code snippet? So we need to truncate it. Max length equals 42. Fill in the blanks in the following paragraph about transformer model types. Something transformer models are encoder only. Examples include BERT, Alberta, Distilbert, etc. The attention layers of the transformer model. So auto-encoding transformer models are encoder only. Examples include BERT, Alberta, Distilbert, etc. The attention layers of the transformer model consider all words in the input when processing each element. Something transformer models have a something architecture and specialize in text generation. So autoregressive models, transformer models, have a decoder-only architecture and specialize in text generation. These models are essentially feed-forward models that generate the next token in a sequence based on predicted probabilities given the preceding elements. Sequence-to-sequence models are encoder-decoder models and specialize in tasks that involve transforming one sequence of data into another, such as translation, text summarization, and generative question answering. T5 and BART are examples of a couple such models. Nice-ish. Carbon footprints of transformer models. In this article, you learn an often overlooked fact about transformer models. They can emit an awful lot of CO2 into our atmosphere. You also learn more about how to monitor and mitigate their emissions. What we'll be learning. It's easy to picture AI as an ethereal, abstract entity living in the cloud with no footprint in our physical reality. However, it's simply not true. A machine learning model, like any other computer program, runs on physical hardware powered by electricity. Deep learning models in general are transformers, and transformers specifically have a tremendous appetite for data and computational power. As a result, they consume a vast amount of electricity during both training and inference. Unless that electricity comes from zero emission sources that translate to a significant amount of greenhouse gases released into the atmosphere. In this article, we'll learn more about the sources of these emissions, ways machine learning engineers can limit carbon emissions in training, and how to monitor and evaluate the emissions of machine learning models while we develop them. AI's present-day danger. As of this article's writing in November 2023, most public discussion of AI's impact is about imagining the near-term future. We're warned that AI might take our jobs, rule over us, or even convert our entire planet into a paperclip factory. However, AI is causing actual, provable harm right now by releasing significant CO2 emissions into the atmosphere. Transformers are contributors to the greenhouse effect that is dangerously warming our planet. One of the first papers to broach the subject, Energy and Policy Considerations for Deep Learning in NLP, puts it like this: recent progress in hardware and methodology for training neural networks has ushered in a new generation of large networks trained on abundant data, which, depending on the availability of exceptionally large computational resources that necessitate similarly substantial energy consumption. As a result, these models are costly to train and develop, both financially and environmentally, due to the carbon footprint required to fuel modern tensor processing hardware. In other words, lots of computation equates to lots of energy with a cost we can measure in dollars in environmental impact. According to Stanford University's AI Index 2023 report, training GPT-3 required the emissions equivalent of about 500 flights from New York to San Francisco, which in the grand scheme of things actually is occurring very often. Like 500 flights from New York to San Francisco, the equivalent amount of flights that's happening, like, that's a fraction of every day. And I know I'm not trying to be like regardless, I'm not going to sugarcoat it. Like 500 flights from New York to San Francisco is pretty minimal, but granted, these things are just going to keep accelerating. So, but I mean, it's hard, right? Regardless, released in 2020, GPT-3 is generations behind the state of the art for large language models, and that's the point. Though the current leading LLMs are closed source and their footprints are unknown, leading open source models can provide us with some helpful approximations. Below, we can see the training time, power consumption, emissions of the 4 varieties of Meta's Llama 2 model. So GPT-3 had 502 CO2 equivalent emission in tons. CO2 equivalent. So Llama 70B had, so total for Llama 2 is about equal to GPT-3. So you can see it's comparable to GPT-3's footprint, over 500 tons of carbon dioxide released during pre-training. Pre-training large transformers is resource intensive, and hosting and serving them via API also requires significant resources. See section 4 of the paper. I mean, really, I just want to say, like, if you think about it, it's so normalized, right, how much energy gets used nowadays. But 500 flights from New York to San Francisco, even the amount of energy it takes to do one of those is like insanity in the grand arc of like how much energy was expended 1,000 years ago, or even 500, or even 300 years ago. But anyway, see section 4 of the paper, estimating the carbon footprint of Bloom, a 176 billion parameter language model for breakdown of these impacts. There's also been growing interest in quantifying the emissions created by model inference. Even though it's smaller than the carbon footprint of pre-training phase, model inference happens far more frequently and hence can add up to a significant amount. A recent paper by Lucioni et al. Titled Power Hungry Processing, What's Driving the Cost of AI Deployment, examines the relative costs of many different model inference tasks and finds that content generation tasks are the most energy and carbon intensive ones. The following figure demonstrates one of their key results, comparing the average quantity of emissions generated by 1,000 queries, each of different transformer-related tasks. How to limit your ML emissions. Energy consumption at this scale has a serious impact on the environment, As machine learning engineers, researchers, developers, and users, it is our responsibility to think through what we can do to limit the harm caused. Thankfully, reducing carbon emissions from transformer usage is not only possible but relatively straightforward. An ML model's carbon footprint is in large part determined by these main factors: the overall size of the ML model we're using, the energy source of the data centers used for the model's training and use, the way the hardware used in training was manufactured. Many deep learning models come with a variety of sizes to choose from. For instance, these, while reaching for the most powerful model for all your tasks is natural, many common operations can be solved by smaller models, conserving resources and reducing your emissions. Careful selection of your data center is another high impact strategy. Consider the following chart, taken from researcher Dr. Sasha Luccioni's tutorial on transformer emissions on Hugging Face. As you can see, Swedish and Canadian data centers. Where is that? Canada or Sweden? I don't see Sweden. Produce only about 2% and 4% of the emissions of those in India, even for the same training run. That's crazy. Another useful strategy involves adding a small amount of custom training data to an existing model to customize it for your purposes, commonly called fine-tuning. By fine-tuning pre-trained models instead of training new ones from scratch, you achieve your intended performance for a small fraction of the computational resources it would otherwise require. In this way, fine-tuning existing models can help significantly cut down on emissions. Finally, there are machine learning strategies you can use to conserve energy too. For instance, take care when choosing your method for optimizing your hyperparameters. Algorithms such as grid search, which tests every possible hyperparameter configuration within a given space, use a great deal of resources running and rerunning the model to test its performance. Instead, using a more limited strategy such as random hyperparameter search can yield equally effective results with far less energy. Tools for tracking carbon output. Thanks to the work of some conscientious ML engineers, we now have several tools to help us calculate the emissions impact of a variety of ML models. This ML emissions calculator, for instance, will output your estimated CO2 impact given hardware type, hours of training, cloud platform, and data center location. Let's give calculating our emissions a try. Say you trained a model on, so it wants me to use this calculator. Okay, I'll honestly, interesting, right? Don't have the time right now. What time is it? 4:30. Okay. I respect it though. What's my next steps? Congratulations on completing Intro to AI Transformers. So we could do Intro to PyTorch, which I've done, or building these. So really what I want to do is put on a hoodie because I'm cold. But in addition to that, what I want to do is, don't need an intro to Hugging Face. Fine-tuning transform models is what I want to do. Don't really have the time for it though. I guess I can make it work. I'll be right back. Let's get it. So, I'm gonna throw these on. So we're good. Oh, there was a view. Let's go. So beta fine-tuning transformer models. Let's get it started. Here. Okay, introduction to fine-tuning. It's a brief introductory video. You'll learn the difference between pre-training and fine-tuning, the appeal of fine-tuning over pre-training. Bring in the audio. Right there.
Welcome to an introduction to fine-tuning. We previously dove into the intricacies of transformer models and the magic that makes them tick. Building upon that foundation, this course is designed to guide you through the process of fine-tuning a pre-trained transformer model, empowering you to create a specialized transformer tailored to your needs. In this course, we'll cover an introduction to fine-tuning in practice, the fine-tuning lifecycle, GPU usage in deep learning, an introduction to PEFT, or parameter-efficient fine-tuning, a review section, and finally, a project. Before we jump into the process of fine-tuning, let's quickly review what pre-training and fine-tuning accomplishes, as well as why each step is important in the development of transformer models. The first step in this important two-step training process starts with pre-training. This is when a transformer model is trained on a massive dataset with a language model objective, such as translation, text generation, or summarization. At this step, the model is learning general language patterns and context. However, it's important to note that this stage is an extremely resource-intensive process, requiring significant time, money, and resources to process the sheer amount of input data. Once the model has developed well-rounded, generalized capability in this problem domain during pre-training, it's time to customize it into a more specialized model via fine-tuning. This is the stage where the model can be adapted or fine-tuned for specific tasks using a smaller set of data. The underlying concept of fine-tuning is that the knowledge gained during pre-training on a large dataset can be transferred to improve performance on a more specific task using a smaller dataset, hence transfer learning. A notable advantage of transfer learning lies in its ability to circumvent the entire pre-training step. By grabbing a pre-trained model and fine-tuning it for a specific task, we save valuable time, money, carbon, and all the headaches from training the base model. And while pre-training is extremely computationally expensive, fine-tuning is possible to do on prosumer and less expensive hardware, making it feasible for users with limited resources to create a transformer model tailored to their specific needs. Now that we've discussed the why, we'll go over the how, starting with the next lesson on the applications of fine-tuning in practice.
Fine-tuning in practice. In this video, we will dive deeper into the differences between pre-training and fine-tuning as regards data and model size, learn some typical use cases for fine-tuning transformers, briefly introduce instruction fine-tuning, a vital technique for chatbot assistance.
We mentioned in the previous lesson that one advantage about fine-tuning is that you need less data than pre-training thanks to transfer learning. But now, we'll put that data reduction into perspective. To kick things off, the GPT-3 research paper, Language Models Are Few-Shot Learners, reported that pre-training GPT-3 175B used a massive 570 gigabytes of data after filtering, which amounts to 3,640 days of compute. In comparison, one of the most popular fine-tuning datasets you can find is the Yelp Reviews dataset, measuring in at only 5.22 gigabytes uncompressed. This is only about 0.92% of the training dataset, yet fine-tuning a general transformer on the Yelp Reviews dataset helps improve its output for tasks like sentiment analysis and text generation due to the collection of text reviews and associated ratings. Fine-tuning is a very versatile technique that extends across many types of model architectures. We can fine-tune encoder, decoder, and encoder-decoder transformer models, whether they're used with text data, image data, or any other data modality. We can even fine-tune other generative AI architectures, such as diffusion models, for image generation. However, in this course, we'll focus exclusively on transformers. Here are some example use cases for fine-tuning. Fine-tuning a vision transformer on X-rays of various tumors to more effectively classify whether tumors are cancerous. Fine-tuning a text generation model on your favorite author's books to more effectively write fanfiction in their voice. Or fine-tuning a sentiment analysis model on your company's review data to more effectively classify future reviews. Fine-tuning is a great way to provide value to a business as an ML engineer. For instance, a company may spend a lot of money calling the APIs of proprietary AI models like GPT-4. A skilled engineer can fine-tune a smaller, open-source model on the company's data that can meet or even exceed a proprietary model's performance on a specific task. In addition to saving money, this approach is more private and secure, as it doesn't involve sending data to a third-party servers. Before we close out on this lesson, we should briefly cover one relatively new type of fine-tuning, instruction fine-tuning. Instruction fine-tuning can teach a text generation model to specifically follow instructions by showing them examples of users asking questions and assistants helpfully solving their problems. This type of fine-tuning was a crucial ingredient in the creation of ChatGPT and the subsequent AI boom.
Just want to read that. Teach a text generation model to follow instructions by showing them examples of successful question answering. This type of fine-tuning was a crucial ingredient in the creation of ChatGPT and the subsequent AI boom. So take a pre-trained large language model, show it some question-answer pairs. So for example, what's the capital of France? Answer is Paris. How far is the Earth from the Sun? 93 million miles. And this leads to an instruction fine-tune large language model.
While the details of instruction fine-tuning are beyond the scope of this course, it's good to be aware of it. What you'll learn in this course will serve as a strong foundation for learning instruction fine-tuning.
The fine-tuning life cycle. This video will cover the following topics: the most important steps of the fine-tuning life cycle, including defining the problem, preparing the data, model selection, hyperparameter tuning, training, testing, and validating, deployment, and serving to users, good resources for obtaining data and selecting pre-trained models.
The fine-tuning lifecycle is very similar to any other machine learning workflow, with only some slight differences. In this video, we'll guide you through the process of fine-tuning a pre-trained model by breaking it down into approachable steps. Typically, fine-tuning involves these steps: defining the problem, acquiring, wrangling, and pre-processing the data, selecting the model, tuning the hyperparameters, training, testing, validating, and serving. Before diving into fine-tuning, it's important to clearly define the problem you're addressing. What type of task do we want better performance out of a general transformer model? Whether it's sentiment analysis, generative question answering, or another task, a well-defined problem points us in the right direction. Once the problem is defined, the fine-tuning dataset needs to be obtained. Like any machine learning project, data is key. You can often find good datasets on open source platforms like Hugging Face or Kaggle. If you can't find any suitable datasets, then you may need to acquire them through methods such as text scraping, and then clean them up by using data wrangling and pre-processing techniques. Now that the dataset has been obtained, we need to figure out what model to feed it into. This step is the main difference from training a model from scratch. Instead of training with the general goal of learning language patterns and context, we need to select a base model to improve upon. A good starting place will be to search for models that perform well on benchmarks related to your desired task. However, when choosing a base model, it's also crucial to consider the computational resources available to you, because larger model variants demand more compute. The step right before we start fine-tuning is tuning your model's hyperparameters, which influence the model's behavior and performance. Examples of hyperparameters include learning rate, batch size, epochs, and weight decay. There are powerful tools that can make tuning easier, such as grid search, Bayesian optimization, and population-based training. By taking advantage of transfer learning during fine-tuning, only a few training epochs are typically needed, reducing the amount of time to complete hyperparameter optimization. However, due to the reduction of epoch needed, overfitting is a potential concern when compounded with the smaller fine-tuning datasets. With your model, data, and hyperparameters in place, it's time to conduct training, testing, and validation. During the training phase, the model is exposed to task-specific data, where it adapts its internal representations and parameters to better align it with the target task. As training progresses, the model learns to extract task-relevant features and patterns, ultimately optimizing its performance on the target task. Following training, the fine-tuned model undergoes testing to evaluate its performance on unseen data. The model's predictions are compared against the test set, and various evaluation metrics, such as accuracy, precision, recall, F1 score, and perplexity, are computed to assess its performance. Throughout this process, validation serves as a step to monitor the model's progress. It involves valuable insights into the model's behavior and guides the fine-tuning process towards the best possible performance. But if the test set is also used as the validation set, then that can lead to overfitting. So it's good to have another portion of the data set aside as a validation set that the model can only see closer to deployment. By isolating this set until the end of the model tuning process, it will serve as a final unbiased test of performance. Finally, if the model performs acceptably, then we can deploy the model into a production environment where it can be used to perform real-world tasks. This process ensures that the model is accessible, scalable, and reliable for end users. Think of fine-tuning as adding one or more layers to an existing neural network. The steps are quite similar to training a model from scratch, because both types of training essentially involve shaping a model to understand and respond to specific tasks.
Cool. What's up next? GPU usage in deep learning. Graphical processing units, GPUs, are a vital component in deep learning. In this video, we'll cover the basics of GPUs and their role in deep learning and fine-tuning. We'll cover the main differences between CPUs and GPUs, why GPUs are so necessary for deep learning, common specifications and models of GPUs, the importance of NVIDIA's CUDA, a software library used to run machine learning code on GPU hardware, as well as its sibling offering from AMD, ROCm.
We've gone over how to fine-tune a transformer model, but what performs the fine-tuning is arguably just as important. We'll be using a graphics processing unit, or GPU for short, to tune our models, so you'll need to be familiar with how a GPU is used in deep learning. In this video, we'll walk you through how GPUs work at a very high level, focusing on context and information that will help you in your deep learning journey. Let's start off this video by comparing GPUs to something you're maybe more familiar with, CPUs, also known as the central processing unit. Both the CPU and the GPU contain a number of individual processing units called cores. Cores are essential components for computing and are responsible for executing instructions and performing calculations. However, cores are optimized differently for the CPU and GPU. CPUs contain a small number of cores. Each core is very powerful and capable of handling complex instructions and operations independently of other cores. If you're not familiar with hardware terminology, don't worry. Imagine a CPU as the brain of your computer. It's really good at doing a lot of different things, but it focuses on them one at a time. Now, GPUs are the opposite. They have huge core counts, but each core can only do simple tasks. Their job is to handle lots of repetitive tasks at once. While each GPU core can't perform complex tasks like the CPU cores, together they can do a lot of work really fast because they all work together on the same task simultaneously. So why do we need a dedicated GPU for deep learning? The large-scale matrix multiplication of neural network training, like the video game graphics from which the GPU gets its name, can be done in parallel with the GPU, dramatically reducing the time it takes to train models. In fact, one of the reasons transformers are presently such a dominant deep learning architecture is because the multi-headed self-attention architecture makes them highly parallelizable. On the right side is a table of consumer and commercial GPU specifications. The last one is NVIDIA's Tesla T4, which is the model you'll be using in the exercise notebook.
Just to read that, so GPU usage in deep learning, the large-scale matrix multiplication of neural network training can be done in parallel. Parallelism dramatically reduces training time. Multi-headed self-attention architecture makes transformers highly parallelizable. And we see the RTX 4090 has a base clock speed of 2,235 megahertz, 82.58 T-flops, and 24 gigabytes memory, and a core count of 512. So I just want to come out here. So if I go to collab, come back here. So it's the A100, change the runtime time, A100, V100, and T4. And we're here, no, here. So A100, V100, and T4. So this is how it stacks up. It's a crazy amount of memory in the A100. Wow. Significantly more memory than the 4090, but its base clock speed is like half. And its FP32 performance, which I don't even know what that means, that's very much smaller. Similar core count, but significantly smaller, really.
Books coming up. But the GPU needs a bit of help from something called VRAM, or Video Random Access Memory. While very similar to your computer's RAM, VRAM is optimized for handling the large amounts of data required for rendering graphics. It's typically much faster than regular RAM, and has a high bandwidth to keep up with the demands of rendering high-resolution images and videos in real time. This is extremely important for tasks like inferencing and fine-tuning large models, as they take up a great deal of memory. Another concept worth being familiar with in GPUs is that of occupancy. Occupancy refers to how much of a GPU's potential computing power is being used at any given time. Low occupancy means an inefficient use of the GPU's power, while high occupancy means you're getting your money's worth out of your GPU usage. There are a multitude of metrics used to assess GPU performance, such as flops, clock speed, core count, VRAM bandwidth and size, and standardized benchmark scores.
So flops, number of floating point operations a GPU can perform in 1 second. Higher flops indicates higher computational power. Clock speed, frequency at which the GPU's cores operate. Higher clock speeds generally result in faster processing of instructions and computations. Core count, number of processing cores within the GPU. More cores generally lead to higher parallel processing capability. VRAM size, amount of memory available on the GPU, impacts its ability to handle large data sets.
In this table, you'll see some of these metrics, along with a description of what they measure and the impact that they have on the GPU's performance. Some of the most powerful consumer-grade graphics cards on the market are the RTX 4090s from NVIDIA and the RX 7900s from AMD. These can get really pricey though, but don't worry, because there are plenty of free cloud-based solutions that democratize training for all. Currently, these offerings mostly utilize NVIDIA's commercial-grade GPUs, like the A100, H100, Tesla V100, and T4. The very last thing I want to touch on is something called CUDA, which stands for Compute Unified Device Architecture. It's a parallel computing platform and API created by NVIDIA. CUDA enables developers to utilize the power of their NVIDIA graphics cards for general-purpose computing tasks beyond just graphics processing, like training a model. In the process of writing deep learning code, you'll often move data to CUDA, so the computation can take place over there. AMD has their own version called ROCm, but CUDA is industry standard, being widely supported on AWS, GCP, and Azure. Unless you seek out this field in deep learning, you don't need to worry about learning how to program in CUDA. There was a lot of information in this video, so let's review what we went over in this lesson before we close out. Dedicated GPUs excel at parallel computing, making them ideal for training transformers due to the multi-headed self-attention mechanisms. VRAM is optimized for handling large amounts of data, which is perfect for handling the input data when fine-tuning. Occupancy measures how efficiently a GPU's computing power is utilized. High occupancy indicates optimal GPU usage. Various metrics like flops, clock speed, core count, and VRAM size are used to assess GPU performance. NVIDIA's parallel computing platform and API, CUDA, is widely used for GPU-accelerated tasks like deep learning.
Cool. What's next? Introduction to PEFT. In this video, we'll discuss the basics of parameter-efficient fine-tuning, PEFT. PEFT enables cutting-edge models to be fine-tuned on consumer hardware, democratizing access to customized LLMs. We'll explore the very basics of low-rank adaptation, LoRa, a way of training a much smaller subset of model weights to conserve computation and time. A brief introduction to quantization, which reduces the overall model size by intelligently reducing the precision of certain model weights. The combination of these two techniques is known as QLoRa.
In this video, we'll introduce the concept of parameter-efficient fine-tuning, or PEFT, and show you a few of the current most popular techniques. To fine-tune the most powerful models available today, it would typically cost a prohibitively large amount of time and money. This is the problem that PEFT exists to solve. It is a set of techniques designed to update model parameters efficiently, thus enabling fine-tuning of models without breaking the bank. We'll explore two key techniques that help us lower the compute requirements of fine-tuning large transformer models, LoRa, or low-rank adaptation, and quantization, as well as their combined approach known as QLoRa, or quantized low-rank adaptation. LoRa stands out as a change from conventional fine-tuning methods. Unlike traditional approaches that update all model weights with newer parameters, LoRa strategically updates only a subset of parameters. This subset is identified through a clever application of linear algebra, which allows for the selection of critical parameters while discarding redundant ones. The linear algebra technique will be covered later in this course, but for now, let's take a look at the visual representation of LoRa on the right. The matrix for the pre-trained weights are on the left in blue, while the two smaller low-rank matrices are on the right in yellow. In a full fine-tuning process, every weight in the blue square on the left would need to be updated. But with LoRa, only the low-rank fine-tuned weights would be updated. These fine-tuned weights act as modifications and are added to the full set of pre-trained weights to get our final representation of weights. Quantization, on the other hand, isn't solely a fine-tuning technique, but rather a method to reduce the precision of numbers in the model's weights. By reducing the number of bits used to represent floating point numbers, models can be drastically compressed without significant loss in quality. A tangible demonstration of this can be seen in the comparison between quantized and non-quantized versions of Microsoft's V2 on Hugging Face. The non-quantized version of the model weighs in at just over 5.5 gigabytes, but quantized versions range between 1 to 3 gigabytes, depending on the amount of precision. The drastic reduction in model size achieved through quantization showcases its effectiveness in enabling the deployment of large language models, even on resource-constrained environments, which can even be run independently of fine-tuning too. Now that we understand the benefits that LoRa and quantization provide, we can discuss Q-LoRa, which combines the two techniques. The process begins by quantizing the model, which reduces its size and computational requirements. Then, LoRa is applied to selectively update a reduced set of parameters within the quantized model. By combining quantization and LoRa, Q-LoRa achieves significant parameter efficiency gains. This two-step process makes it possible for everyday developers with consumer hardware to customize their own large language models. These methods are a vital piece of an ML engineer's toolkit in the current ML landscape. We'll use this cutting-edge technology to fine-tune a generative language model in this course's project, providing you the foundation to perform your own powerful fine-tuning projects on state-of-the-art models in the future.
Amazing. Next. So, to review, we've covered the advantages of fine-tuning over pre-training, the life cycle of fine-tuning as well as its use cases, the uses of GPUs in deep learning and fine-tuning, the basics of parameter-efficient fine-tuning PEFT, including LoRa, quantization, and Q-LoRa. You're now ready to dive deeper into these subjects and develop more hands-on skills in the following lessons.
That was a fairly information-packed lesson, so let's take a bit to review everything we covered. Fine-tuning smaller open-source models on proprietary data can rival or surpass the performance of expensive proprietary models. Besides cost savings, this approach enhances privacy and security by avoiding third-party servers. Fine-tuning datasets are significantly smaller than pre-training datasets, making the process much faster and less resource-intensive. Instruction fine-tuning trains models to follow specific instructions, contributing to advancements like ChatGPT. The fine-tuning workflow is similar to training models from scratch. Each step contributes to shaping the model for the target task, ensuring optimal performance in real-world applications. GPUs excel in parallel computing, which is vital for deep learning and especially transformers. VRAM, occupancy, flops, and clock speed are just a handful of metrics used to evaluate GPU performance. Occupancy measures GPU utilization efficiency, which is crucial for maximizing performance. NVIDIA's CUDA and AMD's ROCm are parallel computing platforms enabling GPU-accelerated tasks like deep learning. PEFT techniques lower the compute requirements of large-scale fine-tuning. LoRa strategically updates critical parameters, while quantization reduces model size without significant loss in quality. Q-LoRa combines the two, achieving significant parameter efficiency gains. Now that we've reviewed the essentials, we'll dive deeper into the mechanisms of LoRa and quantization in the following lesson. After that, we'll fine-tune our own models. First, a BERT sentiment classifier, then either Mistral 7b or Distilled GPT-2.
Nice. Let's go. So, real quick, are we done with the videos? Yeah, so take this out. Don't want to do that. Are we still good? Oh, I think we're still good. This looks cool, by the way. All right, anyway, focus. So, introduction. LoRa stands for low rank adaptation and is a technique for efficiently fine-tuning deep learning models. In this lesson, you will learn about LoRa, how it works, and how to use it to fine-tune LLMs. You will also learn about Q-LoRa, or quantized low rank adaptation, which combines an additional technique known as quantization with LoRa to further improve fine-tuning efficiency. Why LoRa and Q-LoRa? While fine-tuning is less resource-intensive than pre-training, it is still a computationally expensive process. The model performance of any deep learning model correlates with the size of the dataset, i.e., bigger the training dataset, better the model. But large deep learning models contain a huge number of pre-trained weights, making them memory-heavy and computationally costly. Traditional fine-tuning involves using supervised or semi-supervised learning methods to alter these weights and adapt the model to a specific task or dataset. In the case of large language models like GPT-4 or Llama, where pre-training involves massive datasets, the starting point for fine-tuning is a neural network with billions of weights. Fine-tuning such a model is near impossible without massive amounts of compute. Here's where LoRa and Q-LoRa come in. These techniques democratize access to generative AI and are essential for anyone looking to customize a pre-trained LLM in a cost-efficient manner. The weight matrix. Before getting into the basics of LoRa, let us take a deeper look at what happens in traditional fine-tuning. Our starting point is the weight matrix, which is generated while pre-training a model. Models like the GPT series, Llama, Palm, etc. have a specific type of neural network architecture, the transformer. Model weights in a neural network are numerical values learned during the training process that associate nodes between layers of neural networks. For a typical neural network, this learning process thus results in a matrix of weights, W, where each individual weight is a scalar value. So, Wij, the weight associating input layer neuron I and output layer neuron J. When you hear that a pre-trained model like GPT-3 has 175 billion parameters, essentially, it's 175 billion numbers represented in a weight matrix. There's a significant caveat here, and that is important to stress. Model parameters in transformer models are distributed across many matrices within many layers. For the purposes of our lesson, however, this doesn't matter, as the goal is to understand LoRa and Q-LoRa. The processes are the same for multiple weight matrices as well, and in the interest of keeping it simple, we're going to refer to one weight matrix. Fine-tuning the weight matrix. Fine-tuning a deep learning model involves updating the weight matrix by training it on a small data set. This boils down to figuring out what to add or subtract from the original weights so the model is better adapted to the new data set. In general, fine-tuned weights equals original weights plus weight update. The original weights are represented by the weight matrix of the pre-trained model, W. The Greek letter delta, represented by a triangle, is often used to denote increments or decrements from a value. It's thus appropriate to represent the fine-tuning adjustment to the original weight matrix W, or the weight update, as delta W. Mathematically then, the whole fine-tuning process can be written as follows. So weight of fine-tuning is equal to original weight plus delta weight, where weight of fine-tuning stands for the fine-tuned weights. The above equation seems simple enough, but in practice can get arbitrarily expensive. For a model like GPT-3, for instance, this involves updating 175,255 million parameters, which is just a fancy way of saying 175 billion parameters. Such a task is impossible resource-wise for a small startup or university, let alone a scrappy developer. Decomposing the weight matrix. LoRa is a technique that reduces the number of trainable parameters by decomposing the weight update matrices into smaller matrices or low-rank matrices and expanding them back mathematically to the size of the original weight matrix. This technique was introduced by researchers at Microsoft in a landmark paper released in April 2022. You can access this paper. Let's check it out. LoRa. Save that. Goodness. Back to this. With LoRa, instead of fine-tuning the 175 billion parameters of GPT-3, one would be fine-tuning 37.7 million parameters, almost 5,000 times smaller. We'll get into how LoRa does this in the following exercise. So the notebook to the right provides a visual representation of the weight matrix and what a weight update for fine-tuning looks like in matrix format. Once you're done browsing through it, click next to move to the next exercise. So here we see, let's look at a simple example of how to construct the weight matrix. The following figure shows a simple neural network with 3 layers, an input layer, a hidden layer, and an output layer. The input layer has 3 nodes, and the hidden one has 4. Because of this, there are 12 model weights here represented in a 3x4 matrix. So the fact that there's 3 represents the inputs. The fact there's 4 represents the hidden layers, nodes. So 3x4. For a large neural network like a transformer, we can extrapolate this matrix to look as follows. The weight matrix below has m rows and n columns and is an m by n or mn matrix. The total number of elements in this matrix is mn and corresponds to the size of the transformer model, often expressed in billions of parameters. So here we see m1, m2, m3, m4, all the way to mn. Size of model equals number of model parameters equals mn. The equation, fine-tuned weights equals original weights plus weight update, now looks as follows in matrix form. So here we have the original matrix, fine-tuned weights ft. So this is the matrix after fine-tuning. So we take the pre-trained weights, right, mn, this matrix mn, and the delta w, which is the weight update. So the delta w for all these weights. Low-rank adaptation, a linear algebra interlude. Transformers use massive matrices that are computationally difficult to work with, but with some linear algebra, we can actually speed things up by expressing all the information of the big matrix in 2 smaller matrices. If you're not familiar with linear algebra, do not be apprehensive. We will cover the 2 main concepts we need to understand LoRa, which are rank of a matrix and matrix decomposition. Rank of a matrix. Consider the following matrices. So we have matrix A, matrix B, matrix C. Rank of matrix A is 2, rank of matrix B is 1, rank of matrix C is 2. In matrix A, the third column, call 3, is exactly twice the first column, call 1. One way to think about this is that the third column adds no new information to the matrix. In matrix B, call 1 and call 3 are multiples of the middle column. All the information, so in matrix B, call 1 and call 3 are multiples of the middle column. All the information within the matrix is pretty much contained within one column. Matrix C seems unlike the prior two. It doesn't look like any column is a multiple of another, but there's a sneaky way to still get all the information in column 3 by combining the prior two columns as column 3 equals 2 times column 2 minus column 1. Ahahaha. Above are 3 different examples of linear dependence between the columns of a matrix. Linear dependence means that a column in a matrix can be represented as a linear combination of the other columns. Some columns are exact multiples of others, as in matrices A and B, or they can be combinations of other columns, as is the case with matrix C. The rank of a matrix is the number of linearly independent columns in a matrix. Matrix A has 2 linearly independent columns and a rank of 2. Matrix B has 1 linearly independent column and hence a rank of 1. Matrix C has 2 linearly independent columns and thus has a rank of 2. Matrix decomposition. Now that we have an intuition for matrix ranks, we can look at how it allows us to decompose big matrices into smaller matrices. There is a theorem in linear algebra known as rank factorization theorem that states a matrix of size Mn can be written as the product of 2 matrices of sizes Mr and Rn respectively, where R is the rank of the matrix, so long as R is greater than or equal to 1. We can understand this with an example. A 3 by 3 matrix of rank 1, like B above, can be decomposed into 2 matrices of size 3, 1 and 1, 3. So here we see this original matrix. We only take the middle column, and we're only taking the first row. The following exercise will explain how all of this relates to fine-tuning transformers. Before that, we will demonstrate the above using NumPy. So calculating matrix ranks. Calculate the ranks of matrices B and C and store them as variables rank B and rank C respectively. Print them to see if they match the pre-predicted values. So NumPy, or numerical Python, is a Python library that allows us to perform numerical operations on arrays of numbers with Python. NumPy's linear algebra module, linalg, enables us to perform operations on matrices. The function matrix rank in this module calculates the rank of a matrix. Run the following cell to get a demonstration of how it works. So import NumPy as np, a equals NumPy array, 132408510, print rank of a, print numpy.linalg.matrixRank of a, and it gives back 2. So rank of a matrix. Calculate the ranks of matrices B and C below and store them as variables rank B and rank C respectively. So rank B equals, what is it, np.linalg.matrixRank B, is that it? And so np, where am I? So yeah, np.linalg.matrixRank A, yeah. So cool. Rank C equals np.linalg.matrixRank A. And then print them. Matrix decomposition. We're now going to examine an example of matrix decomposition. Let me just save this and test it. Below are 3 matrices, W, P, and Q, which are all rank 2. The NumPy library allows us to multiply matrices using the @ symbol. For instance, the product of B and C matrices in the previous checkpoint would be B at C. We will check if P and Q are rank decomposed matrices of W. Create a matrix S. That's the product of P and Q. So P at Q. Create another matrix, difference matrix. That's W subtracted from S. I don't think this is the right way to do it, but we'll see. Print both to ensure that S and W are the same matrix. Oh, nice. Oh, not nice. W subtracted from S. I see. To ensure that S and W are the same matrix. Oh, okay, yeah. Cool. All right, save it, test it. Suppose the W matrix in the previous checkpoint was the weight matrix in a large language model. So we're supposing that this in the previous checkpoint was the weight matrix in a large language model. This is a slightly ridiculous assumption given that the typical large language model has huge weight matrices with dimensions in the order of millions or even billions, but let's go along with this for a minute. Recall that the number of training parameters of the neural network is the same as the number of elements in the weight matrix. To calculate this, let's print the shapes of the weight matrix W and the decomposed matrices P and Q. So 5, 5, 5, 2, and 2, 5. The number of parameters in W would be W params equals 5 times 5 equals 25. The number of parameters after decomposition would be the sum of the number of parameters in P and Q. Calculate this and store it as the variable total params after LoRa. So the sum of the parameters in P and Q. So 10 plus 10. Let's see if it works. Okay, it might seem like, so scaling this calculation for LLMs, it might seem like rank decomposition didn't make much of a difference in this case, but let's look at what happens when these numbers get as big as they are on your average LLM. Consider a LLM with 256 million parameters. For comparison, BERT has about 340 million parameters. The weight matrix has a shape. Weight shape equals 16,000 by 16,000. Suppose the rank of this matrix was 300, and W is decomposed into two rank 300 matrices, P and Q, similar to the math we did above. Can you estimate the number of parameters to fine-tune after the decomposition? I don't know. So if the rank of, what are these ranks? I don't know. What is it? So shapes of P and Q would be, I see 16,000 by 300 and 300 by 16,000. So the total number of parameters after decomposition would be 16,000 times 300 plus 300 times 16,000 equals 900 or 9.6 million. 9.6 million is quite a bit smaller than 256 million. Very true, very true. Implementing LoRa to fine-tune LLMs. We're ready to put together what we've learned in the last couple of exercises to understand how LoRa can be used with LLMs. LoRa reduces the number of trainable parameters for fine-tuning in 2 steps. Instead of adjusting the weights directly, LoRa copies the weights and records the difference, delta, between the original weight matrix and the fine-tuned model. This difference matrix is referred to as the update matrix. Delta W equals the weight fine-tuned minus the original weight. It reduces the size of this updated matrix using low rank adaptation by decomposing it into 2 smaller matrices. So delta W M times N equals A M times R times B R times N. In other words, if the update matrix has a size Mn and rank R, it can be decomposed into matrices A of size Mr and B of size, and B of size Rn. A and B are smaller than the delta weight matrix, but they become the delta matrix's size when multiplied. This process reduces the total number of trainable parameters, making fine-tuning way more computationally cheaper. Here's a table adapted from the original LoRa paper that shows exactly how much smaller it is compared to other fine-tuning methods. So we see regular fine-tuning, 175 bil. LoRa R equals 2, 4.7 mil. LoRa R equals 8, 37.7 mil. LoRa implementations randomly initialize A and B and populate the values during training. We must also guess the optimal rank to project the update matrix onto. The value of R in this problem is a hyperparameter. Very small values of R yield excellent results, as shown in the table above. So on the Wiki SQL dataset, so accuracy only decreased by 0.4 and actually went up by 2 compared to regular fine-tuning. And on this other data set, accuracy actually increased again. Is that right? Fine-tuning accuracy percent on 2 data sets. Wow. Pretty cool, pretty cool. I mean, I guess it makes sense, or does it? I don't know, but it's truth. So, very small values of R yield excellent results as shown in the table above. The smaller the R value, the lower the computational and memory costs needed for fine-tuning. Note, what makes this possible for LLMs? Conventional wisdom tells us that in the case of LLMs, the bigger the size or number of parameters, the better the model. However, this appears to contradict LoRa, which is about reducing the number of trainable parameters to at least an order of magnitude smaller than the pre-trained model. What makes such a thing possible for LLMs? How does this not result in diminished performance? The answer to these questions lies in the concept of intrinsic dimensions of LLMs. In 2020, a group from Facebook published a paper, link there, demonstrating the following. A pre-trained large language model can and often is a full rank matrix with high dimensionality, i.e. huge M and N values. However, such a matrix can be optimized for fine-tuning tasks by projecting this onto significantly lower dimensions. They define intrinsic dimensionality as the minimum dimension needed to solve the optimization problem it defines to some precision level. This paper paved the way for methods like LoRa and QLoRa, which reduce the dimensionality of the pre-trained LLMs. What's this paper? Intrinsic dimensionality explains the effectiveness of language model fine-tuning. Save that. Copy this. So again, though, the matrix can be optimized for time projecting this onto significantly lower dimensions. They define intrinsic dimensionality as the minimum dimension needed to solve the optimization problem it defines to some precision level. This paper paved the way for methods like LoRa and QLoRa, which reduce the dimensionality of the pre-trained LLMs. This is an image demonstrating the steps for a full fine-tune versus LoRa. The full fine-tune graphic to the left shows how the weight matrix W is updated using the update matrix delta W, which is as big as W. So our model input, pre-trained weights, plus weight update delta W goes to the model output. However, LoRa demonstrated on the right side of the image uses rank decomposition to decompose the update matrix delta W into smaller matrices A and B. The total number of parameters needed to train is much smaller here. So we have the pre-trained weights W, and we're adding to it the A and the the A and the B to the model output. Quantization. Another way to reduce the computational demands of fine-tuning is to reduce the precision of the weights in a pre-trained transformer model using a technique called quantization. To understand how this works, we'll examine what numerical precision means here and how it relates to different data types in Python. Numerical precision of weights. We know that the weights of a neural network are numbers represented in a matrix. These numbers are represented with three components: the sign, the exponent, and the mantissa. Just random fact, mantissa is my favorite word in mathematics. It's just a fun word. It's a beautiful word. So anyway, we know that the weights of a neural network are numbers represented in a matrix. These numbers are represented with three components: the sign, the exponent, and the mantissa. So -1 to the sign times mantissa times base exponent. We can understand this with an example. Consider a possible weight value, -5,963.776. In decimal notation, i.e. base 10, one would write this as follows: -5.96377 times 10 to the 3. Here, the sign is 1, since it's a negative number. The exponent is 3, and the mantissa is 5.963776. In a binary system, i.e. base 2, which is often typical of computational systems, this number would be -1.456 times 2 to the 12. Each of these numbers, the mantissa, the sign, and the exponent, are represented as bits or binary digits that require storage space in computational devices. Numerical precision then depends on how much space can be allocated to the mantissa and exponent in representation. The overall sign always requires exactly 1 bit. The more memory available, the higher the precision of the number that can be stored. Data types in NumPy and PyTorch. Different numerical data types in Python allot different amounts of memory to store a number. Since deep learning involves working with large arrays of numbers, our choice of data type often involves significant trade-offs. For instance, more memory implies higher precision, but it also means less space on computer hardware to store larger arrays. Additionally, if a data type allotted more memory for the exponent, we might get a higher range of values, meaning less precision in the mantissa value. Some common data types used in Python are listed below in descending order of precision. Floating point 32, FP32, float 32, uses 32 bits to store a number, 1 for the sign, 8 for the exponent, and 23 for the mantissa. Floating point 16, FP16, or float 16, uses 16 bits to store a number, 1 for the sign, 5 for the exponent, and 10 for the mantissa. Signed integer 8, int 8, uses 8 bits and can only store integers. Since one of those bits is for the sign, there are 7 bits available for the absolute value of the number. Unsigned integer 4, uint 4, uses 4 bits and can only store positive integers. In a base 2 number system, the range of numbers that can be stored is from 0 to 16 to the 2 to the 4. Factorial? Wait, no. Oh, okay, yeah. So the range of numbers that can be stored is from 0 to 16. So 2 to the 4 factorial. Or 2 to the 4. Why is there an exclamation mark there? I think that's, regardless. Computer memory is often written in units of bytes. A byte consists of 8 bits. A FP32 number requires 32 bits or 4 bytes, usually full precision in deep learning jargon. FP16 requires 2 bytes and is referred to as half precision. Int 8 requires a single byte, and uint 4 only half a byte. If we were to convert a large array of float 32 numbers to int 8, we'd reduce the amount of memory needed by a quarter. This is precisely what quantization does. We're going to implement quantization first with NumPy, and then using Hugging Face. We've preloaded a NumPy array numbers in the setup cell. The attribute dtype gives us the array's data type. The attribute item size gives us the size of an item in the array in bytes. Run the setup cell to examine both. So, data type float 32, bytes needed per element 4. Changing data types in NumPy. We've written some code to convert numbers to an array of floating point 16 numbers using the type np.float16 function. Run the cell corresponding to this to examine how the numbers change. Apply the np.int8 function to numbers in the following cell and store the result as an array int8 numbers. Create a variable int8 bytes per element and set it to the bytes needed per element in this new array. Print both values to examine the output. So back here, preloaded NumPy array below. The attribute dtype gives us the array's data type. The attribute item size gives us the size of an item in the array in bytes. Run the cell below to examine the output. So import NumPy's np numbers equals numpy.array. With these numbers in it, data type equals float32. Print data type numbers.dtype. Print bytes needed per element numbers.item size. So the data type is float32 and the bytes needed per element is 4. Checkpoint 13, changing data types in NumPy. We've written some code below to convert numbers to an array of floating point 16 numbers using the type np.float16 function. Run the following cell to examine how the numbers change. So now all of these numbers are restricted to, at least we can see, no more than 3 decimal places. And in the case of something like this, it got rounded down. So bytes needed per element 2. Note that the precision has already gone down. Now, similar to the above, you can use the int8 type in NumPy, np.int8, as a function to convert its element to the signed integer data type. Apply np.int8 function to numbers. So let's do int8 numbers equals, so np.int8 numbers, create a variable int8 bytes per element, and set it to the bytes needed per element in this new array equals int8 numbers item size. And then we're going to print int8 numbers, print both values to examine the output, bytes needed per element, if I can spell it right. So now we have 1, 2, 3, 7, and 15, and bytes needed per element is 1. Quantization in NumPy, let's just save this and test the work. We will assume that the original array numbers in the previous checkpoint represents weights in a deep learning model and test a toy function to quantize it. While the above method converted the values in the numbers array to integers, it could be better. It merely rounded down the numbers to get an integer value and lost some information in the original array. For instance, if all the weights were numerical values, less than 1, np.int8 would round them down to 0. To do justice to the original array, we'd need to account for its range of values relative to the range of numbers that the data type can represent. We've written a simple function in the cell below to quantize arrays using a type of quantization known as abs-max quantization. Run the cell to define the function. So reading that again because I didn't really digest it. So we'll assume that the original array numbers in the previous checkpoint represent weights in a deep learning model and test a toy function to quantize it. While the above method converted the values in the numbers array to integers, it could be better. It merely rounded down the numbers to get an integer value and lost some of the information in the original array. For instance, if all the weights were numerical values less than 1, np.int8 would round them down to 0. To do justice to the original array, we'll need to account for its range of values relative to the range of numbers that the data type can represent. We've written a simple function in the cell below to quantize arrays using a type of quantization known as abs-max quantization. Run the cell to define the function. So def quantize x, scaling the value, scale equals 127 divided by the max of the absolute value of x. Quantized value equals scale times x dot round, return quantized value dot s type np.int8. Apply this function to the array numbers and store the result in quantized array. So quantized array equals quantize numbers. Print the array and its item size to examine the results. Just gonna come up here and steal this. Yeah, quantize array dot item size. What is it again? Yeah, item size. Cool, save that and test it. It's pretty cool. So it turned, oh, I see. So we've successfully quantized an array from a float32 array that requires 4 bytes of memory per element to an int8 array that requires only a single byte per element. What would it mean to do the same for a large transformer model with huge weight matrices? How much would the computational memory of the model decrease? Luckily, we can answer these questions very easily with Hugging Face's Bits and Bytes library. The documentation for this package is available at the following link. We've already written some code below that calculates the memory footprint of distilled GPT-2, a lighter version of the GPT-2 model. Run the following cell to view the model size in bytes. So from transformers, import auto model for causal LM, auto tokenizer, import torch, torch.manualseed 19, model ID equals distilled GPT-2, model equals auto model for causal LM from pre-trained model ID, print model size in bytes, model.get memory footprint. Add 2 more arguments to the from pre-trained method to get the 8-bit quantized version of distilled GPT-2 as follows. So that's a crazy size. It's big size. Was that 3 gigabytes? Regardless, add 2 more arguments to the from pre-trained method to get the 8-bit quantized version of distilled GPT-2 as follows. Set device map to auto. So for our int8 quantized model, auto model for causal LM from pre-trained model ID, your solution here. So device map equals auto and load in 8-bit is true. And then uncomment the line that prints the model size and run the cell. I thought it was going to be a smaller number, I'm not going to lie. Still significantly smaller though. We're looking at a difference. This is 333,000. This is 127. Sorry, did I say thousand? I meant million. So let's save that. Test the work. Keep it pushing. QLoRa fine-tuning quantized LLMs with LoRa. The two techniques we've covered in this lesson, LoRa and quantization, are ways of making the fine-tuning process more efficient. The former leverages linear algebra to reduce the number of trainable parameters in fine-tuning. The latter cleverly reduces the numerical precision of the model weights to significantly decrease the amount of computational memory needed to store them. QLoRa leverages both of these together to make fine-tuning computationally efficient and inexpensive. It was introduced by Demers et al. In May 2023, and they demonstrated that QLoRa could fine-tune a 33 billion parameter model on a single consumer GPU without any performance degradation. The original paper can be found at the following link. QLoRa combines quantization and LoRa to fine-tune LLMs by freezing 4-bit quantized versions of the pre-trained model weights, implementing LoRa on the quantized model to fine-tune the model. The following table, adapted from Tim Demers' talk here, demonstrates the power of QLoRa. So model T5, 11 billion, regular fine-tuning memory, 176 gigs, fine-tuning memory with QLoRa, 6 gigs, Llama 2 70B, regular fine-tuning memory, 840 gigabytes, and fine-tuning memory with QLoRa, 46 gigabytes. This is significant memory improvement. Specifically, QLoRa introduces two key features to further reduce memory usage. NF4 data type, a 4-bit normal float data type, occupies half a byte per element. Double quantization, quantizing the constants that are within the bits and bytes implementation. Hugging Face's bits and bytes library makes it very easy to implement quantization techniques. Loading a quantized model can be done with a few lines of code. From transformers, import bits and bytes config, model ID equals model of your choice, load the model of your choice, specifying the configuration for quantization. NF4 config, bits and bytes config, load in 4-bit true, sets the 4-bit quantization. BNB 4-bit quant type equals NF4 using data type NF4. BNB 4-bit use double quant equals true with double quantization. Model NF4, auto model for causal LLM. Auto model for causal LLM from pre-trained. Model ID, quantization config equals NF4 config. The Hugging Face hub also contains many already quantized models such as GPTQ that can be loaded for inference. The image to the right demonstrates the two steps involved in implementing QLoRa. Quantization, the left half of the image, demonstrates the implementation of quantization by lowering the numerical precision of the weights. LoRa, the right half of the image, shows the low-rank adaptation of LoRa. Here, the weight matrix is decomposed into two low-rank matrices, reducing the total number of trainable parameters needed for fine-tuning. Together, these two steps make QLoRa a powerful technique for fine-tuning transformer models efficiently. I also want to add, I read an interesting paper yesterday that talked about single bit LLMs. Like instead of having to do even like a integer 8 or a NF4, like a 4-bit single bit LLMs. Don't know too much about it, but I read the paper. It's pretty interesting. Had like over 500 upvotes on Hugging Face. Recommend anybody go read it. I mean, you can check out the video of me reading it live. It's like a couple videos behind this one, but I'll admit I read it at like 5 in the morning. I was very tired and I was trying to be quiet, so it's not the greatest video, but check out that paper. Anyway, summary and next steps. Recap. Nice work. In this lesson, you've learned about two essential techniques of fine-tuning that democratize access to LLMs, LoRa and QLoRa. Here's a quick recap. Fine-tuning can be computationally expensive as transformer models have huge weight matrices. LoRa and QLoRa are techniques that minimize the compute power and memory needed to fine-tune LLMs without degrading model performance. LoRa uses low-rank adaptation to decompose the weight matrix into smaller matrices, thereby reducing the number of training parameters. Quantization is a technique that reduces the memory needed to store weight matrices by reducing the numerical precision of their elements. QLoRa combines quantization with LoRa to achieve significantly higher efficiency in fine-tuning LLMs. Next steps, Hugging Face's PEFT and Bits and Bytes libraries. Hugging Face's PEFT library allows one to implement techniques like LoRa and QLoRa with little effort. PEFT stands for Parameter Efficient Fine-Tuning, and you can find extensive documentation for this library in the following link. PEFT contains many methods to fine-tune transformer and diffuser models, making it accessible for developers to customize generative AI models with consumer hardware. Additionally, we've already gotten a taste of the Bits and Bytes library, which allows one to seamlessly integrate quantization into this process. In the coming module, you'll learn how to use PEFT and Bits and Bytes libraries to fine-tune transformer models. You're now ready to learn how to implement these techniques when building your own custom LLM with Hugging Face. The image to the right demonstrates different methods of fine-tuning a BERT, a transformer model, and an LLM. on IMDb data. The first row depicts a full fine-tune that involves altering all the model parameters. So you have a full fine-tune, you take BERT, fine-tunes all the parameters with all of the IMDb data, and you get IMDb BERT. The second row shows fine-tuning with LoRa, where only a subset of the parameters are fine-tuned. So you take LoRa, you take BERT, fine-tunes a subset of the original model's parameters with this data, and then you get BERT plus IMDb LoRa weights. The third row indicates that QLoRa fine-tunes a subset of quantized parameters within the model. So you take the quantized version of BERT, fine-tune a subset of the quantized model's parameters, and you get quantized BERT plus quantized IMDb LoRa weights. Awesome, awesome, awesome. So unfortunately, okay, let's take this. I'm not going to be able to do the actual coding part today. I'm going to do it tomorrow. I have to go, but which of the following statements about GPUs, graphic processing units, is false? Occupancy measures how efficiently a GPU's computing power is utilized, and a low occupancy indicates optimal GPU usage. GPUs have a larger number of cores than CPUs and can perform simple tasks in parallel. CPUs can perform complex tasks, but only one at a time. GPUs use a dedicated memory unit known as VRAM, or Video Random Access Memory, that is optimized for handling the large amounts of data required for rendering graphics. So I believe occupancy measures how efficiently a GPU's computing power is utilized, and a low occupancy indicates optimal GPU usage. So the reason I'm thinking that's false is because what I understood as occupancy to mean is just how much of the processing unit is being used at any one given time. So I guess you could say a low occupancy indicates optimal GPU usage. But I also am pretty sure that the VRAM thing is right, so I'm going to say this is false. Yes, the statement is incorrect. High occupancy implies that GPU is being used sufficiently. Got you. Why is fine-tuning a computationally expensive process? It involves working with an additional data set. No. It involves modifying the weights of a pre-trained model. Pre-trained transformer models are usually huge, and weights are stored in giant matrices that are computationally expensive to store and modify. LoRa reduces the number of trainable parameters needed for fine-tuning by adding adapter layers. No, by decomposing the matrix that updates the weight matrix of the original transformer. I think so. Optimizing input layer activation. So no. Adding adapter layers. No, it's this. LoRa uses low-rank decomposition to decompose the update matrix. Fill in the blanks in the following paragraph about the fine-tuning life cycle. Typically, the steps involved in fine-tuning are 1. Defining the problem, 2. Acquiring, wrangling, and pre-processing the data, selecting the model, tuning the hyperparameters, I believe. Let's get it. Quantization involves converting higher precision data types, such as float64 or float32, to lower precision data types, such as int8 or uint4. Fill in the blanks in the following code snippet that converts a NumPy array from a 32-bit floating point data type to an 8-bit signed integer data type. The snippet also prints the size of each element in the output array to make sure that it is 1 byte each. So we do import NumPy as MP, weights array equals mp.array, the array, something equals float32, so that's a D type. Output array equals mp.something, weights array, mp.item size. No. What are we doing again? Quantization involves converting higher precision data types to lower precision data types. Fill in the blanks following code snippet that converts a NumPy array from a 32-bit floating point data type to an 8-bit signed integer data type. So int8 signed. And then item size. Let's get it. Fill in the blanks in the following paragraph about QLoRa. QLoRa combines the following two methods to increase fine-tuning efficiency. Something, lowering the precision of the weights in the transformer model, that's quantization, and something, decomposing the weight update matrix into two matrices of smaller rank, that's LoRa. LoRa uses low rank adaptation to decompose the intrinsic dimensions of the weight matrix, the weight matrix containing the pre-trained model weights, the update matrix that represents the difference between the fine-tuned model weights and the original model weights. And we're saying again, LoRa uses low rank adaptation to decompose the weight matrix containing the pre-trained model weights. I believe that's right. This is saying the update matrix that represents the difference between the fine-tuned model weights. No, it's this. Oops. not quite. The pre-trained model weights are frozen during LoRa. So LoRa doesn't use low rank adaptation to decompose the pre-trained model weights. LoRa uses low rank adaptation to decompose the update matrix. So decompose the update matrix that represents the difference between the fine-tuned model weights and the original model weights. Which of the following statements about matrix, ranks, and rank decomposition is false? In a 3x3 matrix, if two columns in A are multiples of the third column, the rank of the matrix is 2. So if two columns are multiples of the third column, then no, the rank would be 1. A 4x4 matrix has 3 columns whose elements are all 0. With some non-zero elements, the rank of this matrix is 4. How does a 4 matrix have, I see, it has 3 columns whose elements are all 0, and 1 column with some non-zero elements. The rank of this matrix is 1. I believe so. A 5x4 matrix of rank 3 can be decomposed into 2 matrices of ranks 5x3 and 3x4 respectively. Honestly, I need to I need to learn matrix math. I'm going to go with this, but I was wrong. In a 3x3 matrix, if 2 columns in A are multiples of the third column, the rank of the matrix is 2. So the reason I said that was wrong is because I thought that if 2 of the columns are multiples of a third column, then that would mean that the rank would be 1 because you can reach the other 2 columns by just multiplying the third one. But I guess I kind of have it backwards. So again, I need to get better at that. I'm not going to retake the quiz. So this will be a task for another day. But that other day is probably going to be tomorrow. So